So today I'm teaching about instruction fine-tuning. Right? Now, if you look at all these models, right, that have made this field generative AI popular, ChatGPT, GPT-4, right? They all come with chat assistants. So you can converse with the models. That was not the case before. You have learned about transformers, BERT, other modules. I'll just do a quick recap. They can't chat with you, but these models can chat with you. So what is something different that have happened, right? And the idea comes from instruction fine-tuning becoming one of the main pillars for the success for these models. And what went different was instruction fine-tuning. And then there's a second thing about RL from human feedback that will be covered tomorrow. Right? So today and tomorrow will become the building blocks for what happens, like how do you build models like ChatGPT, GPT-4. Right? And that's why day after tomorrow, I'll talk about all the different models that are there right now. For that to understand, you need to know these two pillars, instruction fine-tuning and RLHF. Okay? So that's what we are doing today and tomorrow. And day after tomorrow, we'll talk about different kind of LLMs that are there, right? What do they use, right? What are these techniques that they use? What is instruction fine-tuning? I'll spend some few minutes on what is that, giving you some motivation, right, from different sources. Before that, I thought let's do a quick recap of what has happened till now. So how many of you are completely comfortable with transformers? Transformers. Right, this is one of the things I typically show from the blog by Jay. The modules in transformer encoder decoder. So you have the self-attention, feed-forward modules, and many other things that you would have learned, right? Multi-head self-attention and everything, right? And then the decoder. Does that go to this? Yeah, may not be visible. So what's the difference between encoder and decoder of a transformer? Which module is different? Masking, okay. And what else? Cross and attention. So you have a cross attention, encoder, decoder attention, and you have a masking, right? And I don't know if we have already told you, this is a very good book, Speech and Language Processing, 3rd edition from Juravsky, where you would find the basic nice chapters around transformers, pre-training, the topics that have been covered. If you want some reading material, that's a very good book. Speech and Language Processing, 3rd edition, Juravsky. It's still in progress, so they didn't have chapter yet on the things I'm covering today. Instruction fine-tuning is not yet written, but hopefully by few months it will be there. It's a very good book for referring to the details. So we talk about this masking, right? If you have any questions around these topics, feel free to ask. Okay. So it's a school. So we want you to at least understand transformers, right? That's a building block for everything that we will cover in this school. And you can do the coding part, and you also understand the details, right? For example, I believe you know how to compute parameters in transformer. Yes? Okay. So let's do a quick, we will do a quick exercise on that. So once you know transformers, the next thing that was covered are pre-training. Transformers has huge number of parameters. What I can do, I can pre-train. I take a lot of data where no human labeling is required, take all the data on the web, and do simple tasks, right? And because transformers is encoder and decoder, I can pre-train either the encoders only, encoder decoders together, or only the decoder. So if I pre-train only the encoders, what kind of models do I get? If I pre-train just the encoders, what was the model that we get? BERT model. I just pre-train encoders. If I pre-train encoder decoder together, I get T5 I get BART. If I only pretend decoder, GPT, right? So they were the very early additions of models that were there. These are all covered in detail. So what is the difference between T5 and BART model? How are they different? Pretending strategy, slightly different, right? So in T5, you don't output the complete sentence, only the span that is corrupted, but you output the entire sentence, right? You generate the entire sentence. And then all of these models have their multilingual variants, right? These are all details. So they will have their multilingual variants. You will have MT5, MBART, MBERT, right? I didn't see an MGPT, but maybe. So we don't have an MGPT, I think. But typically models have a multilingual variant where you just mix more languages. No. So when you have a model, so this next. So then let's see some, I'll do some simple practice problems, right? So that you all, I am comfortable that you know how to compute parameters and other things, right? So let's take this practice problem. So suppose you are taking a T5 large model, okay? Large doesn't matter, it will have more parameters, but that's what we are asking. Now, this has a model dimensionality of 1024. If you don't understand a term, just let me know. Model dimensionality is 1024. Vocabulary size is 32,000. 24 transformer layers. 16 attention heads for all the different kind of attentions that you have. And the feed-forward network has 4,096 nodes. Okay. So how many parameters this T5 large model actually has? So suppose this is the question I'm giving to you, right? So how would you solve this problem? So first of all, let me ask you, I mean, while you're doing this, how do I get the vocabulary size for a pre-trained model? Do I fix it a priori or do I get it by some method? How do I get the vocabulary for a pre-trained model? What will the vocabulary do for me? I'll get the embeddings for all the words. So what does it mean that vocabulary size is 32,000? Number of distinct words, but there will be too many, right? Maybe millions of distinct words. So how do I obtain this vocabulary size? Yes? We fix this. Let's say we say I want a vocabulary size of 32,000. And how do I achieve it? BP. Byte pair encoding. Anybody does not know what is byte pair encoding? Sorry? You know that. Okay. That was also covered, right? Okay. So you get huge byte pair encoding, you get 32,000 byte vocabulary, right? Okay. So then you have everything that you want to know. Then tell me how would I compute the number of parameters I need for training this T5 large model? It's an encoder decoder model. So how many parameters it would have? And whatever you need to know is given here. Yeah, take your time. You can use your rough page, your notebook. Do that. If you have doubts, this is a good time to ask. Yes. How many? Right, that's given by the model dimensionality. So each word will have a 1024 dimension embedding. So ask your questions, right? You may have doubts, but that's where we are doing it, right? You should be able to compute this number of parameters. So position embeddings, whether you will train or not train, let's say position embeddings are not to be trained. So forget position embeddings, right? Sometimes you train them, sometimes you don't, right? You may use sinusoidal or you may train them like embeddings. So don't worry about position embeddings, okay? Otherwise, you will have exactly the same number of parameters as you have for the embeddings. That many will be added. No, not that many. It will be different, right? It will depend on what is the sequence it can take. What's the sequence it can take? So it will be different. So that we have not told here. So don't worry about positional embeddings. Okay, what are the three blocks where the parameters will have? What are three things? Embedding parameters, then encoder and decoder. So first try for 1 and 2, and then you can do for 3. So by the way, whatever I'm writing on the board, is that visible or do we have to turn on the light? Is that visible? Black marker? Thanks. Anyway, nothing important here, just embedding encoder decoder. And this thing, I guess you understood. Next, I'll only write with black. So the first person to answer will get some bonus. So ACM wants some top 2 students from the school. So we have to give some 2 names to ACM. So this may get added up in how we are counting. Some additional motivation. Yes. We are not asking you for positional embedding, so it won't matter. Only if you have to find out the number of parameters for positional embeddings, you need the sequence length. Okay, do we have an answer? For embedding? Embedding is 32 million, but encoder? Yes. T2768. For what? Embedding or encoder? Embeddings, right. So embeddings, parameters, you have 32,000 vocabulary. For each, you need 1024 dimension embedding. Roughly 33 million in embeddings. What about encoder? So you get the embeddings, you feed the embeddings. What are the additional parameters? Right? So there are 24 layers. What does it mean? There are 24 encoders. How much? Overall in encoder? 68 million. Okay, let's see. So one answer 68 million. Any other answer? Yes? 52 million. Any other answer? Yes? 25 million. Three answers. 1.2 billion. Did you say billion? Okay. Any other answer? 367 million. You see, we have all ranges. 100. It's okay. Approximately 100 million. 100 million. 34 million. 84 million. 155 million. 65 million. 300 million. No two questions have the same answer. That's what is interesting, right? As if we are having a chat model here. So you can converse the way you want. Like that's the problem with dialogue agents, training dialogue agent. You can have as many responses as you want. That's somehow not true for this question. Yeah, it will have one answer. Okay. So it will have one answer, right? You don't want diversities, but it's okay. Yeah. And that's okay. That's fine, no problem. I'll tell you how you can compute it, and then you can say where you went wrong, right? Or what you did not assume that I am assuming. Sure. 6 million. Okay. That's a very small model for this. 6 million. Okay. Any other answer? 264 million. So you are here. 264 million. 198. 192. 67, you're close to this. Approximately. Approximately. Okay. Sure. Should I then do that? Which one of these is correct? Okay. And please remember your answers, and please remember who has given what. Okay. Sure. So let's try. Okay, and you tell me if I'm making a mistake, because I can very well make a mistake, but you have to correct. Okay. So fine, transformer, let's say one encoder, right? Only one encoder. If I know for one encoder, I can multiply by 24. Yes, easy problem. So one encoder. So one encoder, what will do? It will take this 1024 dimension input. Let's call it D. Model dimensionality D. Okay? D is 1024. Okay. Next. What will happen next? I'll have multi-head attention. Yes. So let's think about how many heads are there? 16 heads. So H is 16. There are 16 heads. For single head attention, what are the parameters? Q will not work, W is better because you have a query. No? So W K, W V, W Q, three matrices. W0, yes, I'll also add that, W0, good. Now, what are your next thing is, what are the dimension of your query key and value embeddings? Yes? Divide by 16. So each query key value dimensions are model dimension divided by number of heads. And that is 64. So each query key value is 64 dimension. I can use D by H or 64. Okay? Anybody got that wrong? No. Okay. Fine. So then, what are the dimensions of WK? It will transform the embedding into, it will project the embedding to D by K dimension, D by H dimension. So this will be D times D by H. It will project 1024 to 64 dimension. Query matrix, and you have to ask questions whenever you're not sure. Okay? You have doubt, you have to ask questions. All have the same dimensions, D times D by H. So that means in WK, WV, WQ, we get, so how many parameters we have got? 3 times D squared by H. In just computing query key value matrix. Okay. Now, W0 will come later. First, I will talk about multi-head attention. This was single head attention. Now, multi-head. So how many, what I will multiply it with? H, 16. So this is for multi-head attention. Any problem? Okay, good. Now, what does WO do? What will WO do? What is the role of WO matrix? It takes, so each attention output will be D by H dimension, right? 64 dimension. And you will have 16 such outputs. And then you apply W0 matrix. It will convert it to model dimensionality. It actually right now also model dimensionality, but it also makes sure there is some combination, some connection between different attention height outputs. So, and you get a final, you get back your model dimensionality, D. So what is the dimension of W naught? Yeah, because D by H times H is D. So D times T, D cross D. So W naught is D times T. So you add that. So till now, what you have done, self-attention, multi-attention, and W naught will take a simple model dimensionality output. What happens next in an encoder? Feed-forward layer. Good. So now I'll take this and put a feed-forward, which will then, and finally it will come back to D. So things always come back to model dimensionality in transformer, right? You deviate them and bring them back to model dimensionality. So what is this? What is the dimension of this feed-forward network? There are 4096 nodes. So it's 4D, right? It's 4D. And then you bring back D. So how many parameters you're having in the feed-forward layer? 4D square plus 4D square, 8D square. Yes? So 4D square plus 4D square. And this was how much? 4D square? Attention at 4D square parameters, and feed-forward has 8D square parameters. And that's all. There will be some layer normalization and things like that. They're minor things, bias terms. But then you can say each encoder has 12D square parameters. Okay. So each encoder has 12D square parameters. And let's not do the calculations right now. Let's wait, right? Be lazy, like mathematics, be lazy. Keep on putting in terms of these variables until finally you have to compute it. Okay. So then there are how many encoders? 24 encoders. So I say, okay, into 24, 288. Yes, 288 D square. Now you have to go back to calculator and compute what is that. 288 into 1024 into 1024. Anybody can try that? Which is the closest answer? 300 million? Okay, so who gave 300 million? 300 million? Oh, yes. No, no. In encoder decoder, you don't have that. In encoder decoder, in the encoder, you don't have any final layer. Okay, so no. That happens only when you are doing something with the encoder. Here, encoder will not do anything, it will just compute representations. The decoder will generate. In T5, the decoder will generate. So you don't have that in the encoder. Okay. So 288 D square, roughly 300 million. Okay. So TH may please note the name of the person who gave that a single correct answer. Yeah. Okay, very good. Anybody has doubts on this? It was not difficult, right? Okay, but no problem if you're doing for the first time. Now, next question. If this is the number of parameters in encoder, what is the number of parameters in decoder? Okay. So again, yeah, you can still give an answer next. What is the number of parameters in decoder? Don't worry about final layer right now. Okay. Without it, just in the layers, decoder layers, how many parameters will be there? No, you don't have to add embeddings. No, you can if you are taking the final. No, embedding we are adding. No? So here we have embedding 33 million, and this is 300 million. I think 301 million. So 334 million becomes by adding embedding. Did you give the answer? No, no final layer. Is the embedding layer plus all the encoders. Actually, final layer has the same number as this, because final layer, what you do, you apply V, right? Yeah. That's true. But you see, do you understand now? You don't need that in this T5 encoder decoder. In encoding, you're only computing the representation. You're not doing anything on top of the final layer. In the decoder, you will need this. Okay, when you go to the decoder, you will need this. In the encoder, you don't need that. Okay, this plus this. Now, decoder, number of parameters in decoder. Now, you don't have to redo everything. Just see what will change. And I asked that question to you before. What is the difference between encoder and decoder? And you answered, right? So it's a slight difference from the encoder. Yeah, what was the difference? Encoder, decoder attention, right? So it will have at least this many, plus how many more? Yes. 411? Okay. So decoder, we are getting 411 million. I'll wait for some more answers. Yes, 411. Okay, this time we are converging. Okay, 411 again. Yes, any last answer? 402. Okay. Now this is slightly better. Huh? Which one is correct? Any other answer? 340. 340. 370. Wow. 378. 378. 480. Okay. Okay, but at least things are in the range. 400 exactly. Okay. It's like 402. 402. Okay, many are getting 402, 400. Okay, nice. So 30. 30. Okay, let's see. So what will change in the decoder? So when you will decode a token, it will have the embedding, D-dimension embedding. Then you will anyway apply the self-attention. Same parameters already added. Plus, you will also do it encode decoder attention. So how many parameters? So in encode decoder attention, where is the query key and value coming from? Queries from here. And key and value are from the encoder. The final representation of the encoder. Right? They're coming from there. So I'm just doing another self-attention. If you think like that, how many parameters will be added? The same parameters that you needed for self-attention. How many were those? You will need WQ, WK, WV, and WNO. Right? So you need 4D square more parameters per encoder. So I'll need per encoder 12D square plus 4D square, 16D square. No, multi-iteration with W0 gives you 4D square. So you have to also take into account the W0, right? Same thing will happen here. You have this query key value and the W0 matrix. So that's why you will have 4D square. Okay. So that's why you get 16D square. Because transformer is completely a modular architecture. You don't want to make these changes. If self-attention is using W0, this also will use W0. Okay. So 16D square, and if you see how many will be added, there will be 4 by 3, right? So roughly, so all these are 400, 402 are the correct answers. Okay. Sure. And the person who gave the first answer, right? 400, 402 together. Okay. So TMA kindly note. Sure. So then total there are 734 million parameters roughly, right? Now what happens from the final layer to the, you can have another 33 million parameters if you want from final layer to predicting the vocabulary again, right? In the book, they mentioned people have also tried unembedding layer. They use embedding and put it back, but let's not worry. There is something called unembedding layer, where they will just use the same embedding parameters. They tie them with the final layer. It also happens. That way you will not need this additional 33 million, but yeah, in the worst case, you will need this additional 33 million. So, okay, very good. Any questions? So right now we'll say 734 million is the parameters, right? Only in the encoder decoder. Okay. So this was the solution that I anyway did on the board. Okay. Sure. Ready for another question? Another practice question? So this is on self-attention. This should be easier, but still I just want to make sure. So suppose you are passing two words, thinking machines, to a transformer encoder. Okay. And the input dimensions are just 6. Okay, right now don't worry about these things we taught here, just to understand self-attention. So there are 6 dimensions each, the input, and for the first attention head, just think about the first attention head. The query key and value will take 2 dimensions from the input each. Okay. So what will be the query projection for the first word? 0, 1. Query projection for the second word? 1, 1. Next two will be key, and last two will be value. It's just a simplification for the question, right? That's not exactly how things happen, but let's say this is how you are computing your query key and value. Now, if you do that always, what are the weights of your query key and value transformation matrices? Is the first question. If you always take the first 2 dimensions of the word as your query, next to as key, last 2 as value, what is the weight of query transformation matrix? So what will be your WQ? 2 cross 2? No. 6 cross 2 matrix, right? 6 cross 2. And what will be the values? Right? So it will be 1, 0, 0, 1, and all zeros. Right? You multiply it with this, you get only these 2 as your output. You multiply this with this, you get the first 2 elements. It's a hypothetical thing. That's not how things happen, but yeah, just for this case. Okay. You have to learn these matrices. But anyway, that's why A part is not so important, but you get that. B part. What will be the self-attention output for the word machines? So they're thinking machines. So machines, what will be the self-attention output? You're using a scaled dot product. A scaled dot product. So what will be the attention output for the word machines in this case? -1. Attention output for the word machines. So the query will come from machines, right? Mhm. So yeah, anyway, do that and tell me what is your answer. Two-dimension output. Right? Root 2 plus 1 by root 2 minus 1 by root 2. 1. Mhm. Okay. Minus 1 by root 6. You also got minus? No. Both are same, right? Minus. So both of you got minus. Okay. Right? Two different answers. Yeah, but two same answers also. Yes, at least one more answer. Try. You want to change your answer? Huh. Root 2, comma 1 by root 2. Minus 1 by root 6. Diverse answers again. I have given you all the query key values. Oh. Okay, should we then see what is the correct answer? Okay. 0.784, 0.108. Right? Okay, I can't immediately see if it is one of these, but let's see. Right? Okay, so what will you do? So you have the query key and value, everything. So yes, how do you compute self-attention? What is the first step? So this query, you multiply with all the two values, sorry, two keys, right? So Q dot K divide by square root of dimensions. What are those dimensions? Which dimensions? Key dimension, right? So dimensions of the key. So this will give you, so 1, 1, 1, 1 will give you 2 divided by square root of 2, and 1, 1 to 0 minus 1 will give you minus 1 square root of 2. This is QK divided by square root of DK. So I think some of you did DK as 6, divided by 6. It should be divided by 2. Do you know why? It depends on the dimensions of the query key and value, not the final dimensions, okay? So this is the output at this point. Then next, what will you do? Multiply the value? No, first you have to do softmax, right? So this is square root of 2 minus 1 by root 2. Okay. And take a softmax. I don't know if anybody tried that. May not be so trivial, but I think I have it. I can just show it. So you get square root 2 minus 1 by square root 2. You take the softmax, you get 0.89 and 0.11 after taking softmax. Okay. But then, what is the final answer? I do a weighted average of the values depending on the softmax. So final answer will be, suppose this is X and this is Y, then these are my values. So my answer will be X minus Y and Y. Right? X minus Y and Y. And this in this case is 0.78 and 0.11. And I think this is the correct answer. I think others did not compute softmax, right? So only here you did softmax. Okay, TH may note the name again. Who got the answer? Okay, sure. But let me pause. Is there something you did not understand about this? Yeah, sure. Sure. Did you understand this part? Softmax? Softmax is 0.89 and 0.11. What will be the final output? This means this much weightage you will give to the first word, and this much weightage you will give to the second value. Because what is the self-attention output? It's a weighted average of the values. By softmax, by attention, you get the weights. Now 0.89 times this plus 0.11 times this. So this will be 0.89 minus 0.11, 0.78, and 0.11. Is that clear? Any doubt on this? How we computed the output of scaled dot product attention? Great. Did we also talk about, when you do decoding, what are the methods of decoding? In transformers decoder, when you decode, what are the different ways you can decode? How do you decode? How does decoding happens? Okay, there's no question on this? No further question? We can move forward. So how does the decoding happen? This is the last point in recap that I'll take. How does the decoding happen? Let's say you have a decoder. So what happens in decoding? So decoding happens in an auto-regressive manner. Do you know what is auto-regressive manner? One word at a time. Yes. So when you're decoding for the first word, you started with the start of sentence token, and you obtained a vector. What is the dimension of this? First of all, you will get the d-dimension vector. The final decoder representation, model dimensionality. Next, how will you decode it into a word? What do you do? To decode this into a word, to generate a word, what do you do next? You apply some layer. Yes. So you apply a layer that will give you what is the dimension of this layer? Vocabulary size. Okay? Vocabulary size. And right now, these are all numbers, and you want to convert them to probability distribution. We are called logits. At this point, there will be some numbers, say 0.5, -3, everything is possible, 2, 0.1, whatever. Vocabulary size vector, right? Next, you apply softmax, convert that to probability distribution. How do you generate a word? You have a probability distribution. How do you generate a word from here? Take the word with the maximum probability. So there you take the word with the highest probability. And what is this decoding called? Greedy decoding. It's a greedy decoding. You are taking whatever the maximum probability word, generating it. And then this word, whichever has the maximum probability, will go next as the input token. You'll take its embedding and continue. That's what's called auto-regressive generation. One word at a time you will generate. Okay? Now, this is greedy decoding, right? What is the problem with this? Your model is trained. Let's say your model is trained. Now, what will happen if you apply greedy decoding always? And that's okay, but what is the problem with that? What's the problem in taking the highest probability word? Yes? It's okay, words with same probability, you may still do some tie breaking. You're saying what happens if the first word is wrong? Okay. So this is one problem. What if the first word is wrong? The error will propagate. To avoid that, what do you do? Teacher forcing happens only in training. Okay. Never do teacher forcing in test time. So I remember like 5 years back, I had a student. So he came back with saying, sir, I got better numbers than SOTA for machine translation. And we were all very excited, of course. And we found out the teacher forcing was on during testing. So very common mistake. Okay, teacher forcing is only used in training. Don't teacher force in testing. Okay, yeah. So, anybody who does not know what is teacher forcing? It's okay. We can talk about it very briefly. So what happens? So there's a training phase, there's a testing phase. So when you train the models, you have to compute loss, you have to backpropagate, train your parameters. So when you're training your decoder, same situation. Let's say you computed this probability distribution, right? What will be the loss? At training time, what will be the loss? Cross entropy, what is that? Minus log probability of the correct word. Yes? So that means the ground truth word. Because you are training, you know what is the word you have to generate. So you compute minus log probability of that word, that's a loss, right? You compute loss. The question becomes, my model is not yet trained. It will generate arbitrary probability distributions, right? So then the word with the highest probability may be some random word. So what word will I give with the next sequence token? Will I give the word with the highest probability? I can, but rather what I do, I give the ground truth word. Because I know the ground truth word, so I can actually say, okay, let's put the correct word here. Why do you want to put the word with the highest probability? Because this is wrong, everything will be wrong in training. So in training, you can always put the correct word here and then start decoding. This is called teacher forcing. You force the decoder to use the correct word every time at the input. And you understand if you put the teacher forcing on during testing, what will happen? Every word will be correct, except maybe the last word. Yeah. So this is called teacher forcing. It's only used during training. Okay, let's come back. So this is greedy decoding. You only use the highest probability word. It may be wrong. To avoid that, what you can do, maybe your first prediction is wrong, everything is wrong. To avoid that, what do you do? Beam search. You do beam search decoding. So one option is you do beam search decoding. So don't generate one word, you take top 5 words and continue exploring from these top 5 words, right? And every time you only maintain top 5. At the line, you take the maximum probability sequence. Most optimal is take all the possibilities, right? No, beam search takes more time, but it generally gives you better results. Okay. So in terms of computational complexity, greedy search decoding is the optimal. Greedy search decoding, because you just take the highest probability word, generate it. You don't have to worry about top K sequences. Beam search will take more time. So beam search decoding is an option. That is one problem with greedy decoding. What is the second problem with greedy decoding? The first one may go wrong. What is the second problem with greedy decoding? So the problem is first generation may be wrong, or any generation may be wrong. So use more generations. Don't commit. Don't commit to the most probable word. You still keep track of some top 5, top 10 words and continue. What is the other problem? No, you tell that again. If a word. That's a different problem altogether. Like how do you deal with long context and all? No, that's difficult. Okay, that's difficult. Beam search will be slightly better than greedy in that case, at least. But the other problem that you're not saying, once the model is trained, it's completely deterministic, right? So for the same input, you will generate the same output. No variations. Does GPT-4 does that? Gives you different output every time. So what are the other alternatives of greedy decoding? Where you can do variations. You can produce variations. Beam search is also deterministic. But it can help with the problem of maybe some generation is wrong, so everything is wrong. It can help there. But it cannot help with the deterministic problem of greedy decoding. So what are the other possibilities? Have you heard of, somebody said sampling, nuclear sampling? Have you heard that terms when you are trying to generate huge models? Nuclear sampling, top K, top P. Temperature. What is temperature parameter? What is that doing, temperature parameter? I change temperature, something happens. What is temperature doing? How? So temperature, some idea comes from thermodynamics. If you have a high temperature, explore more. Low temperature, you don't explore too much, right? How is that actually implemented? Temperature? Right, so where does it happen? In this, where does that happen, temperature? Softmax, right? So what you do in decoding, so random sampling with temperature is what it's called. So suppose U1 to U, so these values are U1 to U vocabulary, right? So what you do in random sampling with temperature, so in softmax, you will do exponential ui divide by t and summation exponent uj by t for all j in your vocabulary. So divide by t. By default, t is 1 in softmax. So if you put t less than 1, what will happen? The words that were having high probability will get even higher probability. The difference will increase. Rich will get richer, right? So t less than 1, rich gets richer. It's actually that. It's actually that. I mean, if you don't want to explore at all, you will just do greedy decoding. Then you will take the highest probability word at always, right? So yeah, that's the next thing, top K sampling. So that's the top K sampling. So you have a good idea, right? I mean, why do we change temperature? Why don't I take top K and randomly take one of these? That's what happens in top K sampling. What you do in top K sampling, in this probability distribution, you take the top K words, right? And then normalize them, their probability, and then sample from there. Okay? I'll give you one problem so that it becomes very clear. Third is nuclear sampling, where what you do, you take the words such that their probabilities add up to some p. It's a variation of top K. Rather than taking top K words, you take top few words such that the probabilities add up to p. And then you randomly sample from this. Okay. No, otherwise, how would you sample? I mean, you do normalization so that you can sample. Okay, I'll give you a problem and then you tell me what was your doubt. But you had another question? P is a hyperparameter you set. It's a nuclear sampling. Top P is also called nuclear sampling. So it's a hyperparameter, how much it will be less than 1 always, right? So let's take a simple example and we have to understand this. So what happens? So suppose you have a vocabulary of size 5. Only 5 words in your vocabulary. Okay? And bring the output, the logits are these. 3 minus 1, 2, 1 minus 2. Okay? So let's see. If you're doing a greedy decoding, what will you generate? The first word. You take softmax, this will have the highest probability. Generate the first word, always. What will happen if you do random sampling with temperature 0.5? What exactly will happen? Random sampling with temperature 0.5, what will happen? See, you can do random sampling with temperature 1 versus 0.5. What is the difference? Random sampling with temperature 1 versus 0.5. So random sampling with temperature 0.5. Yes. So first of all, you'll divide by 0.5. So we'll do a soft max over 3 by 0.5 minus 1 by 0.5, 2 by 0.5, 1 by 0.5, and minus 2 by 0.5. So softmax over 6 minus 2, 4, 2 minus 4. Okay? And this will be e to the power 6 by g, e to the minus 2 by g, 4 by g. And g is summation of all this. Versus what would have happened if you take temperature 1? It will be E3 by G, E minus 1 by G, E square by G, E by G, E minus 2 by G. And G is of course different, summation of all this. Do you see what happened now? The difference between this and this word is the probability. This word has e to the power 8 times more probability than this word. Here this has e to the power 4 times more probability than the second word. So the difference in the probability distribution changes. Finally, it's normalized. I don't know what the values will be. Anybody can compute that quickly? If you have not the calculator, maybe the Python, you can just compute quickly. But let's assume, I'm just assuming some values. If you have the actual values, you can put, but let's say this is 0.9. This is 0.02. This is 0.0, notepad. 8. Let's say 0.1. Still not good, but okay. 0. Last one is 0.01. 3.07. Let's see. Approximation is not correct, I know, but let's say the other values. Okay. Now, what do you do when you say random sampling with temperature? You get this probability distribution. It's an approximation, right? But then, how will you generate a word next? Will you take the first word? You will take the first word, pointed probability. Then what did it change? When you were not doing this temperature, in re-decoding also you were taking the first word. After doing all this Jamila, you again got the first word. So what is the benefit you got? Because this will not change the ranking of the probabilities. Yes, that's the name, random sampling. So how do you sample? You just randomly sample from this. But then what is the use of probabilities? Right? Sample proportional to probabilities. Like one simple method is, you put them on a scale from 0 to 1, generate a random number between 0 to 1. Let's say the number comes out with 0.5. So you find out where is 0.5 in the scale. It's here, so you take the first word. If you generate 0.9, I'll generate 0.8, 0.82, 0.92. I'll take the third word. So every word gets generated with the probability that it has. So it's random sampling with temperature. You don't always generate the highest probability word. You sample as per the probabilities. Okay. So this is what temperature 0.5 do. What will top case sampling do here? I'll take the top two and do the softmax. Top two will be 3 and 2. So that means in top two sampling, actually what you do the softmax first, I think. You do the softmax first, then take the top two, and then normalize. So let's say their probabilities will be 0.7 and 0.3. Let's say. No, 0.7, 0, 0.3, 0, 0. With top two sampling. Only first and third one will have non-zero probability, others will have zero probability. Then you randomly sample, so either the first word or third word gets generated. Yes, you don't have that problem that, oh, maybe the least probable word has a chance. This will not happen. Only top few words will have a chance of generating. Is that clear? Why top case sampling is slightly preferred over random sampling? Random sampling, every word has a chance. In top K, only top K words will have a chance. And what will happen in nuclear sampling is very similar. You compute the softmax, take up to the probability 0.5, only those words will get generated. It's very similar, just a different hyperparameter. It's okay. No. See, there are two different problems. Please understand. One is, first word may be wrong. It may propagate. To avoid that, what we can do, don't generate just one word, generate multiple words. And then continue exploring from all of these. That is beam search decoding. Now we are saying the diminished problem. So in the greedy decoding, the highest probability word will get generated. But I want to explore more. I just want to always generate the highest probability word. I want to explore more. So one of the top K will get generated. You are still sampling. So you will sample with these probabilities, 0.7, 0.3. So either you will generate the first word or the third word. Yes, 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 yes. It's a trade-off. It's a trade-off. That's why this nuclear sampling is also preferred. So you say, I will only take the words that will add up to probability 0.5. Then I will normalize their values. Everything else is 0. So low probability words will not even come. Top few words will come. So I think if you do softmax over this comes 0.65 and others come something like that. And if you do p equal to 0.5, only the first word will get selected. So in top P, your distribution will become 1, 0, 0, 0, 0. In this case, you will only generate the first word in nuclear sampling. But this is only for this case. Other cases may be different. In general, you can do that. You can do that. You can put temperature also because you are first doing softmax, so the distribution will change. I really don't know if in practice they do that. In the code, whether they do that. Nucleus with temperature. Maybe they do that. I don't know. Anybody has seen that? With nucleus, do you have temperature parameter also? Okay, we can check. But is there? Nucleus with temperature. So yeah, you can combine them. Okay, let me again ask, is there any question on this? If something you did not understand, you can ask, right? That's why the score is there. If you have some doubt, you can ask. No, beam search is separate thing. Beam search is separate thing. You take top K probabilities in beam search always and continue exploring. In this, you generate one word. You're not going ahead with top 5 words. Like in beam search, what you do? So in beam search, I'll take the top 5 words. And then I'll do generation with each of this independently. I'll take this word and generate again next 5 words. Next 5 words. 5 words. So you get 25. And now among these 25 sequences, you select top 5. And then you go ahead with these top 5 sequences further. Okay. Otherwise, it will explode. 5, 25, 125. So every time you keep it back to 5. 5, 25, 5, 25, 5, 25. K square, K square. That's what you do in beam search decoding. But here you don't do that. Here you always select one word. You're not going ahead with the beam. You will sample. Like, suppose nucleus sampling gives you this probability distribution. 0.1, 0, 0.3, 0.1, 0. Now you first normalize this. 0.2, 0, 0.6, 0.2, 0. Normalized. Now you sample. You put them in a scale. So up to 0.2, 0.8, 1. Generate a number. If it is 0.1, you will select first word. If it is between 0.2 to 0.8, you select the third word. 0.8 to 1, select the fourth word. So you're sampling. It's a random sampling with the probability. Any other questions? Okay, too much of classwork things. We will go back to slides now. So when do we break? 15 minutes. So you want the break now? Okay, so we break now and we'll come back and discuss, come back to instruction fine-tuning. What is that? But you know the last thing I had, the last slide, you know the pre-training fine-tuning paradigm? This has been told in the last 2 days. Once you pre-train the model, you now fine-tune it. Yes, fine-tune the parameters for task specific. So suppose you have fine-tuning, you can fine-tune for sentiment separately, dialogue separately, question answering separately. Right? Different models can be fine-tuned in a different manner. Any doubts around that? Okay. So we will cover a different kind of fine-tuning today. Instruction fine-tuning. This is normal fine-tuning. We'll talk about instruction fine-tuning. Right. Random sampling, yes. How do you generate a word from random sampling? Did you understand this explanation? Suppose these are 5 words. 0.2, 0, 0.6, 0.2, 0 is the probability. You have to generate one word. One way of doing that, put them on a numbers, 0 to 1 scale. So, and generate a random number between 0 to 1. If it is between 0 to 0.2, you generate word 1. 0.2 to 0.8, generate word 3. 0.8 to 1, generate word 4. So only one of these 3 words will get generated. And third word will generate it with the probability 0.6. What is the doubt? See, random sampling. So your random sampling means what? You have to randomly generate one of these 3 words. Now you can't generate them with equal probability. You have to respect the probability values. So you do random sampling respecting the probability values. Was it audible? I'm saying one way of doing that. Put them on a scale and then generate a random number and accordingly generate a word. Any other questions? Okay. So then this paradigm was explained last 2 days, right? Pre-training, then fine-tuning. Pre-train you do with a lot of data, but typically you don't have a task there. So you do it on language modeling tasks, like span correction, you corrupt the span, correct it, like many things you do in pre-training. For fine-tuning, you start from already pre-trained model and slightly change the parameters for a task. So you need more data for fine-tuning. So you can fine-tune on sentiment analysis, classification, things like that. Still, you are depending on data, lot of data, and you are learning the function. This is the input, this is the output, learning some functions, input to output. But I have a good model that understands the language very well. It helps me learn the function efficiently. You can just use a few examples and still learn a good function, right? Now, what is the instruction fine-tuning paradigm? That's a complete, you can say, some sort of game changer, okay? So what is the idea? I'll just quickly show something first.
Sir,
Yes.
sir, during the fine tuning, do we change the parameters only for the layers that we add, or do we change the parameters which have been used in during the pre-training time?
No, there are two options. See, okay, let me just quickly tell it. While I'll let you put that slide first and then I'll. So take T5 model, right? We talked about T5 model. T5 large has say 734 million parameters. Or to even keep it simpler, take BERT kind of model. BERT had roughly 110 million parameters. So you fine-tune BERT for tasks like sentiment classification. What is the input? A sentence, output, whatever sentiment class is, right? So how many parameters you actually need? So when you fine-tune BERT for sentiment classification, how many additional parameters do you need? What do you do? So BERT input is CLS token, and then the entire sentence. And at the final layer, you get representation for all. And typically for classification, you use the embedding of the CLS token. And you classify from that. And from there, you want to classify into 3 classes, positive, negative, neutral. So essentially what can be done, you simply add BERT 768 dimension embedding times number of classes. You can only add 768 times 3 task-specific parameters. Only tune them, and that works, right? Of course, if you have data, you can also fine-tune other parameters that are pre-trained. But what you will do, your learning rate may be different. Learning rate for the task-specific parameters, because they are not trained at all, they are from scratch, may be higher than what you have for the pre-trained layers. There also people have done an experiment. You freeze the lower layers, only train the higher layer. So there are things like that. You do a decaying learning rate. So maybe high learning rate on the top layer and lower learning rates down. So there are many variations. But you can also try this. Just use task-specific parameters, only tune them. Don't touch, just freeze the pre-training parameters. That also works. Okay. So you can freeze them. Only train the task-specific parameters or also train them. Both options are there. Yeah. So this If you don't have sufficient data, this is good enough. If you have a lot of data, you can train the entire thing. But be very careful with the learning rate. Don't use very high learning rates because it's already pre-trained. You want to see in the surrounding of pre-training. You don't want to go very far away from where you have pre-trained. Otherwise, you will have things like forgetting, catastrophic forgetting, and everything will happen. So you don't want to go beyond too much away from pre-trained model. Okay. So instruction tuning, right? This is a nice slides. I took some slides from this tutorial. I'll anyway send that. So this is a nice visualization, right? What is instruction fine tuning? Right? What are you seeing? So how humans learn, right? We don't learn by giving some input-output examples, right? What we are given instead are instructions. Like here, you have to do 41 plus 20. How you are doing it? You're counting by adding tens, right? So 41 plus 10, 51, 51 plus 10, 61. That's how you're counting. And you're given one example, right? In the sheet, it's for the babies. And then they're asked questions like, what will be 52 plus 20? And they are given this sheet. They might not have been given, depending on the age, but then they have to draw this and say, okay, again, 65 plus 30, they have to draw this and get 65 plus 30, 95. So what have you seen here? Instruction, very important. Yes. Task instruction. How to count by tens to add, and where to fill. The instruction is very clearly given. How? In natural language, right? So thing that happened with all this pre-training, models had some understanding of natural language. They started developing this understanding of natural language, right? So you can exploit that. So maybe they will be able to understand instructions in some way, right? Maybe you have to fine tune them for understanding its instructions. They don't understand right now. Maybe you can fine tune them for understanding instructions. Second, very important, just very few examples. The way we learn, nobody gives us like hundreds of examples. Then we say, okay, now 101th I will do. We get only very few examples, right? One example here, right? And then you can do the task. So instruction is very clear. You may be given some example. That's all. Okay, so typically that's how human learn. Detailed instruction, you know the instruction, how to do this task, and maybe very few examples. Very, very few. While even with fine-tuning how the machine learning is happening, you don't give any instructions. You don't give the instruction, you give the input to the encoder, output in the decoder. That's all. Give the input in the encoder and generate the output in the decoder. No instruction. And you need large training sets, become slightly less with the fine-tuning, pre-training fine-tuning. Still, they were large training sets. And even few shots sometimes may need many examples. Or even if it does less, it may not do very well. It may use less examples, may not do well. Okay, another thing I'll tell. So later on. So then the question is, how can these task instructions benefit machine learning? How do we use this idea that humans learn by instructions, very few examples, and can this idea be used for training machines in general in following instructions and using less examples? So what are the instructions? So we all know prompting, right? We give instruction to LLMs anyway, right? They are prompts. So instructions can be oriented towards LLMs directly or towards humans, right? So just to give an example, let's say you have to do sentiment analysis problem. Okay. So here are a few examples. So this was the best pizza I've ever had. 0 means, and only label is given 0, 1, 0, 1, right? What does 0 mean? Positive. And 1 means? 1 means negative, right? Get the better shishi and down the road for half the price, and bad, right? So we are seeing the examples and we are understanding 0 is good, 1 is bad, right? And then you give the new example, excellent pizzas, and all, and you say this should be, label should be 0. Right? It's good. Right? Sentiment is positive. Now, how would you solve this problem with pre-trained models? What do you do? Yeah, but how would you give them 3 examples? How would you feed these 3 examples? And there are a lot of variations in how you will do that. Okay. Let's say you have just the BERT model, BERT, BERT model. Then how would you do that? That's okay, but what would you give to the model? So it will be a classification task. Rather than that, can you think about model having to generate something? Yes, yes, yes. So this, even in like, I can use because this is a masked language model, I can say, excellent pizza, everything, then the restaurant is a blank. And I only care about 2 words, good or bad. So it may generate anything, but I want to see what is the probability for good. I have the distribution. I know the probability for good, I know the probability for bad. And that becomes my point of saying, okay, so good means 0, bad means 1. So what is the probability of generating good? What's the probability of generating bad? I want the probability of good to be higher than the probability of bad. So this was in 2021 pattern exploiting training. So they called these verbalizers. In classification, for each class, you may have certain words that denote that class. Like positive, you have given verbalizers, like good is a verbalizer for positive class, bad is a verbalizer for negative class, right? So that means once you have the masked language modeling, at this point, from the distribution, you only worry about good and bad. You give few examples, and let's see what it will do for the next one. Yes. So in this case, this pattern, it was, and the complete verbalizer becomes a task instruction. Yeah. But there they did not give an instruction as such. They were giving it like you will give it LLM. This is LLM oriented instruction. We know they will do things like this, so I'll give in a particular manner. Now, what happens, right? You're trying to find out how much LLMs know about this, right? By this particular pattern. But what we're talking about is not this. What we're talking about is human-oriented instructions. This was very common LLM-oriented instruction, like whether they know what is in the knowledge graphs, you'll put a sentence and do a masked language modeling, predict the word, does it match knowledge graph? Very many papers that did that. But what is human-oriented instructions? So anybody has tried to develop a data set, try to annotate a data set? Yes, right? So when you try to annotate a data set, you have to actually give instructions to people. Yes, this is the way you will annotate the data set. Very clear instructions, right? And the idea is, can the similar kind of instruction be used for LLMs, large language models, for learning? Right? This was the idea. So we give them detailed instruction, something like this. So Mishra and Wong, so this was a work by University of Arizona and Allen AI Institute together. So they created this natural instructions. So what was the idea? So we will look at a lot of examples. So given an utterance in the recent dialogue context containing the past 3 utterances, output yes if the utterance contains the small talk strategy. Otherwise output no. Okay. And what is small talk? It's a negotiation where you discuss topics apart from the negotiation and build a rapport. And you see the positive example. Fantastic, glad we come to something we both agree with. Utterance, me too, I hope you have a wonderful camping trip. Like he's saying something else to continue conversation. And the output is yes. The participant engaging in small talk while wishing to have a wonderful trip. Negative example, sounds good, I need food the most. What's your most needed item? My item is food too. And the output is yes. This is a negative example because there is no side talk. There is a need for side talk. There is no side talk in this example. So you give a detailed instruction and you give what is a positive example, what's a negative example, right? And now you typically ask people with this input and they have to give an output, right? That's how typically you get the labeling done. So now think about giving this kind of instructions to machines. So we are assuming machines to be humans. They understand language. They have learned language through pre-training, right? And you describe what the task is and how to reach the output from the input. You give everything in the natural language. So given this input, how do you reach output? What are the positive examples, negative example, what you should avoid? Everything you give in natural language. And let them learn from that instruction. Okay. So from the example that we had, so this is the positive and negative example part. So this was only positive example in this case. Some demonstrations are optionally added. And then you have the task instruction. Yeah. So you have the task instruction mapping, and then there are some examples. Okay. Fine. Now, let me now go back to my slides. I just wanted to show this example. This was nice. So I'll now go back to my slide. Idea is that if you can understand instructions, then I can even give you some completely new task and you may be able to do that because you understand instructions. Then even if you are given a new task, you should be able to do this. So for example, when we learn many things in our childhood, right? So how many of you have ever played this game? Anybody? Okay, few people have played this game, right? So how do you learn new games? Somebody tells you what the game is about, the rules, and maybe you see some people playing once. Okay, I'm ready, right? So you know about cricket, you have seen football, you have played that, and you know a new game that's maybe mix up of some games, right? You know how to play different things and you combine that and learn a new task, right? Just by following instructions. Now, similarly, can the machines also do that? That is, let's say we have told them a few things. So this is the input. She chose to make a salad for lunch on Sunday. Question, how long did it take for her to make a salad? Right? And what is the task? Label yes if the sentence contains any grammatical issue, otherwise output no. So answer will be no. List all the words that are essential for answering correctly, like making salad. Answer the provided question based on the given something. And there may be some seen task and there may be unseen task. Label the type of temporal phenomena, like event duration. So what you're seeing, think about this input and output only. Is the mapping very apparent without the instruction? It's not apparent. Until you give the instruction, it's not clear that you have to output a no here. You don't know it's a grammatical issue task, right? Unless the instruction is given. So you learn it from many, many examples. But if the instruction is given, you can learn it instantly. You can know that instantly, right? So typically the way we learn is something like this. I am given an input, my output is a function of the input. Now, how do I find out the function? Either it can be a deterministic thing that I know the function, I can just code that. You give me input, I'll give you output. But in machine learning, what do? You learn the function. So learn F from data. And there pre-training helps because you already have a very good idea of function will be around this pre-trained model. You start from there and learn the surroundings. What's a good function from your data? Input, output examples, what's a good function? That's what we do, right? Now, what's the problem with this approach? This is not sample efficient. You need a lot of samples for this approach. Why? Because now let's go back. How is the data created when you create the data, typically? Like I asked, how do you annotate the data set? You write some instructions. Based on instructions, you have the input and the output, right? But when you learn a model, what do you give? Only the input and output. The instruction is not there, right? So use that to create the data, but when you learn a model, you learn from input to output, a mapping from input to output, and instruction is not in the picture anymore, right? So we don't use instructions while training our model. And that is where, like if suppose this is the question, or this is the task, input is, she chose to make a salad for lunch on Sunday. Question, how long did it take for her to make a salad? Would you think about answering no? No. You don't even know the task. You have to learn from many examples, what was the mapping, and you may give a good function. But right now, you don't even know the task from this example. So, but if this is given to you additionally, label yes, if the sentence contains grammatical issue, otherwise label no, then you will be. Now the question is, can I directly give this kind of instruction to the language models right now? So can I take BERT model or BART model and give them this kind of instructions right now? Yes or no? Yes, tell me, answer, no problem. Right, you can do only if, see, the thing is that we have learned from instructions, but they have never learned from instructions, right? So for giving them this kind of instruction, they have to learn from instructions. That's where the instruction fine-tuning comes in. You train them to follow instructions. And when you train them to follow instructions, you can give them some new task instruction, they will still do that. That's the main crux. Right now, they are not trained to follow instruction. You give them input, output, they learn the mapping. But if they know language sufficiently well now, so if you train them, fine-tune them for learning instructions, they can follow instructions. This is what is called instruction fine-tuning. You fine-tune them for learning from instructions. Okay? Yes. Right, because it has been trained for that. So all ChatGPT, GPT-4, they are trained with instruction tuning. Remember, first thing I said in the morning, for understanding that you need two things. One is instruction fine-tuning. Second is reinforcement learning from human feedback. Today, I'll talk about instruction fine-tuning. Tomorrow, Professor Mosam will be coming. He'll talk about reinforcement learning from human feedback. Together, you get the chat assistants. First part is instruction fine-tuning. Okay? So you have to fine-tune them for following instruction. And then you can say, okay, write me a story about this, and they will follow your instruction and write your story. Yes. You have to train with very diverse kind of instructions. You should not be very restrictive in training. We'll come to these things. There are many variations. Yeah.
Is instruction fine-tuning capable of mitigating that? Like if I just want a yes or no answer, like I think that we're not allowed to write anything else. It still does in the current change. So does fine-tuning actually lead to those applications? Like for humans, it's like if you ask me a question, you ask me a yes or no question, I just say yes or no. But with LLM, it's not that.
Yeah, I know, because the instructions are quite diverse. Sometimes you are also asked to give explanations with the answer. So while generating, sometimes you also give explanations. That's a typical problem with chat assistants. Hmm.
From multiple times, observing everything, understand
Hmm.
they were putting the prompt multiple times, and maybe the LLM is expected to understand what the user need is, and then it would give the output according to that. That's something that I've not found to happen.
Like GPT-3, what used to happen when you give an instruction, write me a story about a frog, it may output, write me a story about a postman. I mean, it will not even follow that. It's just predicting the next words, and it can be anything. Sometimes it will follow, sometimes it will not follow. But these models have started following. Yeah, they're not perfect. They're not perfect. They still can't. But at least they will try to output. They do the task, maybe they will do something more. And right, I mean, following in a structured manner is very, very difficult. Right? Like, think about when you restrict their output space, it becomes very, very difficult. You say, give me a summary in that many words. There's a lot of planning involved, that I need to plan my generation such that I complete my sentence in 10 words. It's a thing that they lack. Yes. Because your base models are not changing. Your base models are the same, right? You're using encoder decoder architecture. GPT is completely decoder based architecture, right? So you're still restricted by the same architecture. Autoregressive decoding, right? You're decoding one word at a time. So that brings in a lot of restrictions. But still, I mean, you do a lot in that restrictions, and there are efforts on what do you have to do if you have to really plan something with the generation. It's a very important and interesting field. And go-to model will have the same problem. Guardrails typically are put at the output level, decoder side. Maybe you will see the output before putting it to the user or the next word. You would have some guardrails at the output when you're generating words. Encoder side is difficult. Encoder side is very difficult. It has to be at the decoder side for generation. Okay, coming back. So if you put this instruction, it becomes easier to answer. But the question is, right now they can't follow instructions. They only are trained for giving an input, give me an output, right? So I have to train them for following instructions. Yes. And this will reduce the search space a lot. If I give this instruction and they can follow it, it will reduce the search space a lot. Now, right? That's the proposal that they gave. You learn from instructions directly. Okay. So what is the basic premise? To follow instruction, you should know language, right? Instructions are coming in language. You should have some idea of language, right? So, and this is the idea that all NLP tasks you can describe in terms of natural language. Like talking about sentiment, you can say, okay, is the sentiment of this movie review positive or negative? You give the sentence, is the sentiment positive or negative? Everything in natural language. You describe your task instruction. Translate how are you into Chinese. They are very, very short instructions, But in general, any instruction, detailed instruction, you can write in natural language. So if your model has capability of understanding language, it may be possible to fine-tune them using instructions. Okay. So Alan AI, who actually started this work, so on their GitHub page, they gave this particular motivation that why did they work on this instruction fine-tuning problem, right? And this is what we are also discussing, right? So current paradigms at that time, supervised learning with task-specific labeled examples, right? Your task-specific examples, you learn from that. They are very good, but you cannot generalize to new tasks. You learn sentiment classification, but can I do topic classification? No. Can I do summarization if I learn classification? No. No. So if I'm supervising to solve questions, cannot solve the classification task. On the other hand, if I can equip a model with understanding and reasoning with natural language instruction, if it can directly follow instructions, then it can generalize to any new task. You give me instruction, I'll follow that instruction and do any task. You give me instruction for classification, I'll do classification. Give me instruction for summarization, I'll follow that and do summarization. Because you will tell me how to do summarization in your task. You will tell me how to do classification in your instructions. Okay. And this was the motivation that they had. Now let's try to contrast it with the other kind of learning that we know. Right? Let's say BERT and T5, right? BERT and T5. So what happens in BERT and T5? You have pre-trained a language model. Yes, you have pre-trained language model. Now you fine-tune on task A, classification task. Task A, classification task. Let's say you need task-specific examples and some additional parameters, and you will get one task specialized model. And then you can do inference on task A. That's a typical way things used to happen before. Or you can do prompting. Like GPT-3 also came. So GPT-3, you can prompt. You can prompt, you can get some output. Here, there's no fine tuning. That time there was no fine tuning possible on GPT-3 at all. So you can do few short prompting and inference on any task. Now, what became different in instruction fine tuning? You can instruction fine tune or instruction tune on many tasks. You have task classification, summarization, question answering, and you define tasks and you fine tune, right? Now, when you fine tune, in the input itself, you'll get the entire instruction and the task instance, and the model will give the output. It's learning with the whole task instruction and the input. I mean, the input to the task in the encoder, say if it's the encoder model, and generating the output in the decoder. And now you give any new task A with the instructions, it will do the inference for that. And that was a new paradigm. See, instruction fine-tuning. Okay. FLAN model was one of the very popular models, FLAN-T5, TK instruct GPT. Instruct GPT used RLHF also, but FLAN-T5 TK instruct only used fine-tuning, nothing else, only fine-tuning. That's what we will cover today. Okay. Is the distinction getting clear? So GPT-3, you're not fine-tuning at all. It's pre-trained language model. And you are just doing prompting to infer. Here you are fine-tuning it. You're fine-tuning it with instructions. Okay, you're giving many instructions for many different tasks and expecting that will do well for new tasks. If you just give instructions. See, new layers depends on the task, right? Like here, if you use, because you cannot do instruction fine-tuning with BERT, you have to use BART or T5 kind of model. In BART and T5, you don't have to use any additional task-specific parameters. Encoder, decoder, right? So what will happen? What will you feed? Let's say T5 model. So T5 has an encoder and a decoder. And suppose this was your task. Let's say this was your task. Instruction, input, output. So what you will feed in the encoder, first you'll pass the instruction completely, then you will put the input completely. This is going in the encoder side. Decoder side, you will only say no. And you will fine tune your model. So all the parameters will get changed slightly. You're fine tuning it. Okay. Previously, this was not being passed. That's the new thing that is happening. Now you're passing instruction before your input. And the idea is that for new tasks, you will again pass instruction, and they have been fine-tuned now to learn from instructions. Because they are seeing instruction now in fine-tuning. Instruction, input, output. Give me a new instruction, new input, I will be able to do that. Because I know how to follow instructions. Okay. Previously, they were not able to follow instructions. Okay. This was a very big change. Okay, that is instruction fine-tuning brought in. Yes. Now tell me which GPT you're using. GPT? You cannot fine-tune. Right, you don't fine-tune them, right? Instruction fine-tuning means you should have control over model parameters, you should be able to fine-tune them. Otherwise, you're just prompting. That's prompting. In fine-tuning, you have to be able to change the model parameters. Okay. Otherwise, just prompting. Any other question? Means people fine-tuned it. Yeah, I don't know if now it is available for fine-tuning, but yeah. It's available, right? GPT 3.5 also. We can fine-tune now. But yeah, but it's difficult. It's theoretically possible. Oh yeah, we don't fine-tune, we give it to them, right? API-based fine-tuning. Yeah. Not like we coding and doing fine-tuning. Yeah. I'll discuss. I'll show examples of what the instruction actually contains. But we'll give you all the details you need to do the task. No. Unseen task, you have to give the instruction. At the inference center, you have to give the instruction and the input. So it is learning how to interpret the instruction to do the mapping from input to output. Instruction plus input goes into the encoder, if it is encoder decoder, and output goes into the decoder. Instruction plus input is getting transformed into output. Now, given a new task, you will give the instruction plus input. And now it has learned how to follow instructions. That's the change. From? So in context learning is prompting. In context learning, you don't fine-tune the models, right? You just give some task examples, right? So in context learning will not fine-tune your parameters. You give some prompt. Prompt means what? See, in decoder models, decoder, you are anyway generating one word at a time. So if you give a prompt, it is as if you're fixing some prefix. And then from here, you have to start generating. You fixed some length of the output in the decoder, and from here, you're generating next. That's all is happening. In context learning, what happens? Because of this context, you get some idea what are you talking about. Are you talking about sentiment analysis? What are you talking about, right? There was a nice paper that showed in context learning, even if you flip the labels, you give the random labels, still it does quite well. It's not so important to give the correct output it matters, but not so much, okay? Because from the input, you're trying to guess what is the task and doing it. Yeah. Yes. Yeah, this won't be an example. Let me not even show the slide. So just saying that you are allowed to put things like this in the language now because you are pre-training them with this. So you're allowed to do things, sorry. You're allowed to do things like this because you're pre-training them. Right? I'll tell what are the actual format. Right? So yeah. Prompting, we don't fine tune. Just in context learning. Instruction fine tuning, we are fine tuning the model. Okay, to follow instructions. Now, this is an example from what is the impact of this instruction fine tuning. Just empirically. So you fine tune on many tasks. You have to get an idea. You fine tune on many tasks, instruction tuning, like common sense reasoning. You give the instruction, here is the goal. How would you accomplish this goal? There are some options. And keep stack of pillowcases in fridge versus in oven. And you say keep stack of pillowcases in fridge is how you will achieve it. Now translate the sentence to Spanish, sentence and target is this, right? Like that, you will give fine tune on many tasks. You give the instruction, input and output. And then even unseen task. You have never even fine tuned the model on natural language inference. But you give it directly in the test time. Input, natural language inference, premise, hypothesis. Does the premise entail the hypothesis? And you have an option, yes, not possible to tell, no, and it should answer it correctly, ideally, not possible to tell from this. Now, what they showed, GPT-3 175 billion, GPT-3 model had 175 billion parameters, zero shot. If they do the task, zero shot. Versus they do few shot, versus FLAN model. FLAN is the model they will do by instruction fine tuning. Yes. And then they see, okay, FLAN-T5 FLAN model actually works much better than GPT-3 even few shot because it has been instruction fine tuned. And now given a new task, you just give the instruction. No need to give examples. I mean, no need to give any few shot training. It will do zero shot. It will do nice in zero shot also. Again, from another paper, for example, what do I mean by generalization? So in training, you are training on some task, some seen tasks, and there are some unseen tasks, and there is no intersection. Seen task, unseen task. So sentiment analysis, classification, sentiment analysis, summarization. Two different tasks. No intersection. One is seen, one is unseen. You train on seen tasks, I mean some tasks, and then evaluate on some unseen tasks. And what they have seen, if you give a lot of fine tuning, I mean lot of seen tasks in training, and keep the unseen tasks fixed, with instruction, the performance improves. Okay. This is GPT-3 static, right? It won't change, but this performance improves if you fine tune it with more and more tasks instruction, even if your unseen tasks are not part of seen tasks. Okay. So you're understanding, I mean, think about you are having to do many different possible tasks. Let the model learn how to follow instruction and do certain tasks. You give an instruction for new task, they will be able to do the task better than what GPT-3 is doing without instruction tuning. That was the paradigm. Okay. So how do you represent instructions? So this was from Swaroop Mishra's paper, ACL 22, cross-task generalization. Okay. So you have input-output. That you anyway used to give, input-output, right? Plus, you take some positive examples with explanation why this is a positive example. Some negative examples with explanation, maybe suggestion why this is a negative example, what you can do to make it a positive example. So they had a very detailed schema for instructions. So you give some examples for positive and negative examples. And then you give a title, definition, things to avoid, caution, and a prompt message. All this together they call as an instruction schema. It's a lot, you see, it's a lot. But typically when you do annotations through crowd workers, you give all these instructions. You say, okay, this is my title, definition of the task, things to avoid, caution, examples, and now you give me new data points. Okay. So something like that. So suppose this is your actual instruction in Amazon Mechanical Turk. They will map it to some title, definition, things to avoid, caution, positive example, negative example. So that's how they created this data. They took, because many people have given these instructions, they are available on online, various GitHub pages. They crawl that and map them to these schema. So what is the title, definition, everything, right? And that's how they created a new data set for instruction fine-tuning, right? Where you have all this possibilities. So something like this. So you have a title, writing questions that involve common sense understanding of event duration. That's your task title. Definition. In this task, we will ask you to write a question that involves this, given sentence, and you give more definition, event duration defined as something. Question usually take few minutes and all. Caution. The written questions are not required to have a single correct answer, because some people may take more time than others, right, for doing the same task. And don't create questions that have explicit answers in the text. That means you have to do some common sense reasoning. Since the common sense reasoning task, it should not happen. Your input itself has the answer for how much time it took. You have to guess that brushing will take that much time and so on. Right? Like positive example. Jack played basketball after school, after which he was very tired. And your output is, how long did Jack play basketball? What do you mean by output? What you have to do? Writing question is your task. Question generation is the task. That's why this is the output. You generated a question. Does that follow the template? You need some common sense reasoning. It is not told in the sentence how much time Jack played football. You have to have some common sense reasoning. Okay, how much time he would have played so that he became tired, right? So it involves some common sense reasoning. So yeah, so the question asked about the duration of the event. Therefore, it's a temporal event duration question. Negative example. He spent 2 hours on his homework. Output is, how long did he do his homework? And this is a negative example. Why? It's already given in the question. He did it for 2 hours. It's not a common sense reasoning question. So that's why you see it's not a very straightforward thing. You're given a very specific definition, what things you have to avoid. You should not give a question where the answer is already there in the input. Right? So this is a negative example. We don't want this question as the answer is directly mentioned in the text. And you may provide some suggestion. So you can see it's a very laborious task that the team did. They took a lot of GitHub pages with their instructions, they converted into their format, and then fine-tuned the model with this instruction fine-tuning. And then you finally end with a prompt. So this is your template. You have an instruction definition, then some positive example, negative example, then you prompt. Now, this is what your model will do. This is the input to the model in fine-tuning. Ask a question on event duration based on the provided sentence. And then you give an instance. Yeah. So common instance. So you give the input sentence. Ishtar be the most to marry Nandini if she meets him again. And expected output means this is what you were wanting as the output. That's how you will train your model. So for your model, the input will be this entire instruction plus the input. And this is what you will train it to do. This is what the decoding will handle. How long had they known each other? That's a valid question because this is not given in the input, right? They have to guess. You have to do common sense reasoning and guess. Another input, it's hail crackle across the com and Tara spun to take her seat at the helm. How long was the storm? It's again common sense reasoning, understanding question, and so on. So you see, first they have to design this whole template, many such cases, and then they will fine-tune, instruction fine-tune the models. Okay, let me pause. Are you getting some intuition on how this process was being done? Collecting data set, difficult part, but they collected the data set. Now, how would you fine-tune? I'll give this whole instruction plus the input, and my decoder should output this. And I will fine-tune based on cross entropy loss or whatever loss, right? I'll fine-tune the decoder so that it gives me the correct output. So fine-tuning is exactly what you learned before. What is changing? The input in the encoder. If it's an encoder-decoder model, what is changing is the input. Input comes with the instruction. Instruction plus the task input. Okay, that's the input to the encoder. And you decode. So that's how they have been trained to follow instruction. Because when you chat, you give some instruction. Oh, I want to write a program based on certain things. Then you give some input and then the output, right? So instruction part is very crucial. You give an instruction, input example, and what the output. That is the training happening. Yes. How would it remember? You see? So that's what you're training it. Instruction plus input, and give me the output. Every time. Every instance you have to do this. You don't expect them to remember this. Okay.
Which I keep them balanced, like A is 50%, B is 50%. So this, whatever the model will think is the probability, the prior probability that the existence of the nature is this, but actually it is not there. So by creating the data set, maintaining the imbalancement, how does that affect the model?
They are nice trade-offs. No? I mean, you have learned so much, it's all in your parameters. It's called your parametric knowledge, right? And when you do fine-tuning, it's again going in the parametric knowledge itself, because your parameters are changing, right? But when you're prompting, that is not going into your parameters. Prompting, you're not changing your parameters. That's a new information you're giving. So how do they interact? The parametric knowledge versus the new information that you're giving. It's a very important problem and not so well understood problem. Fine-tuning is, I'm saying, fine-tuning what will happen in fine-tuning? You have a parametric knowledge already. When you fine-tune, you change your parameters. So depending on your learning rates and all, it may start favoring what you did in fine-tuning. If you have given sufficient examples, you have taken learning rate sufficiently so that then it will follow what you did in the fine-tuning. It will follow that. Yeah, see, it doesn't do Bayesian inference. It doesn't do Bayesian inference. It's a simple thing. I mean, what is the next token probability? Given the current input, what's the next token probability is what it has to do, right? And this comes, as I said, from the pre-training, you fine-tune, you again change your parameters only, right? So if your fine-tuning hedge is much more powerful, it will follow that. Otherwise, it will follow the pre-training. So whether you're fine-tuned for many, many examples, right? You have put the learning rate sufficiently high, it will follow what you do in the fine-tuning. Not worry about pre-training part for that particular question, for that particular task. I mean, you can fine-tuning with completely wrong examples, right? completely change, then it will start following that if you have given sufficient examples.
If this kind of data set, the data does not reflect the actual teacher's problem, then what?
I mean, it will learn that whatever you have trained it with. Yes, yes. I mean, the only thing is that you pretend with a lot of data, it's difficult to pretend with completely wrong data, right? So it may have some side channels from which it will learn things, because you pretend for a long from lot of data, but you can still inject some wrong information if it doesn't come too often. Okay, how many tasks did they have? So they had 61 tasks, 193,000 instances. What are the tasks? Verification, long text generation, minimal text modification, classification, incorrect answer generation, question generation. Okay. Across many domains, they had sports, history, news. That's what they did. A lot of different variety of data is what they collected and created this natural instructions. And how do they encode? They will have the prompt, definition, things to avoid, emphasis. I think this is a typo. This is a negative example. This is a positive example. Negation, positive example. Input X and output. That's where you stop. See, this is what will go in your encoder. And then you will generate in the decoder, if you're using an encoder decoder model. If you're using a decoder only model, you'll put this as the prompt to the decoder and you will generate the next thing. And then they showed what was the difference. So if you do multitask learning versus instruction tuning. Multitask learning, you know what is multitask learning? You give multiple tasks without instructions, right? So that the new things that you're testing on are still unseen. So then this is the performance. So 13 means some Rouge score. So 13 with multitask learning, instruction tuning gave to 32 immediately with BART model. So the BART was the base model, pretend BART. Leave one category. So you removed question generation, 6 to 17. GPT-3 without fine tuning was still doing better in this case, but lead one data set when they did and tested on this, they got much better than the GPT-3 itself. Same here, leave one task, they did better. But supervised fine tuning, complete supervised fine tuning was still better than instruction tuning, which is supposed to happen. If you completely fine tune with all the examples, it still does better. But this is happening without any tuning for these tasks. You're not giving any examples, just giving instruction, input, and you get the output. And this was very good performance already, without seeing any instance of these tasks in the train. Like a zero shot. It's like zero shot performance, just with instructions. Okay. Last row. Last row would be, you take BART model and fine tune on these tasks. Take all their training data and fine tune this without instruction. Just supervised fine tuning. This is multitask. That means these tasks are not seen in the training time. You have trained it on separate tasks, but with the instructions. You have trained with instructions on different tasks. We are not using training data of the current tasks on which we are testing. Yes.
So you predict that find this or that might have a probability that the results.
See, this all came with the hypothesis. No? I mean, this motivation that can the machines follow instructions? That was the hypothesis. Like we follow instructions, can machines follow instructions? That's how they designed this experiment. that, okay, I'll use instructions for training the machines, and I'll see what happens if I give instruction for a new task. Can they still perform? And they found they can.
So, like, that, functions of functions of transformer. Majorly, like, the results that we have built upon are all purely experimental. Like that.
That is true. There are some explanations and all, but yeah, there are some papers that come like why in context learning works, why this works. So they do some spatial analysis, but mainly results are experimental, empirical results. Will it not work? Okay. And then they saw what actually contributed, right? Whether it's no instruction was this average 13 performance. And if you put the prompt, immediately it increases. Definition further increases. And then plus positive examples is very good. This is the best. So definition plus positive examples. That's what they found. If you use definition plus positive examples, that's typically good enough. And say question generation, positive examples were very helpful. And they show various tasks, for example, like if you're doing question generation, you need all these. If you're doing classification, just the definition is sufficient. This is the most important part. And yeah, for different tasks, they try to give what are the important parts of the instruction by doing applications and some justification. And somehow they found if you exclude negative examples, that actually help. So without negative example, they got slightly better results. Even with GPT-3, they found the same thing. That was not instruction fine-tuned. If you remove negative examples, it actually was better. So negative examples were not interpreted in a correct manner. I think that's still a problem. That how do the models make use of negative examples is not clear. So negative example would be that is not correct output for the input. Like we saw generate questions, even duration that are common sense reasoning. You generated a question that was asking the information that was already there in the negative example. So they found negative examples are not helping. Sometimes they are even making mistakes because maybe the model is taking it to a positive example somehow.
Understand that.
Really, that's how, you have to understand, this is what you are trying. This is how humans understand. You want machines to understand the same way, but are they on the same level? Are they able to understand, oh, this is the instruction, this is a positive example, negative example. They are anyway making some correlations. That this is what I have seen previously, I will do this. So maybe negative, they are treating in the same way as positive by mistake. If they miss the negative example word, if they don't properly put attentions and all, it may go other way around, right? That may be happening because this is just a complete prompt. So negative examples were actually hurting. So maybe it's not trained properly for handling negative examples. That's the idea. So surprisingly difficult for models to learn from negative examples. That's what they found. And yeah, that's typically the difference between the prompt. So you put the context and ask something, question and options. Here in natural instruction, you'll get the definition, emphasis, prompt, some context, and the question. So here you give much more detailed instruction than you are giving in prompts. So, and they also showed what happens if you increase number of training tasks. If you increase number of training tasks, typically the performance improves with instructions. Full instruction, you see the performance was improving a lot if you increase the number of training tasks. Doesn't happen always with no instruction. There's a slight improvement, but not so much. So that was their aim. Cross-task generalization. Is the term making sense? Cross-task generalization. I'll train for one task and test another task, right? So you're training on some tasks with instruction and testing on a cross task, a different task with instruction. And you are expecting that you will do better. And that's what they found. It happens with instruction fine-tuning. If you increase the number of training tasks, this happens. Because you're seeing diverse kind of instructions. And then they said, okay, it means what happens if I further scale it? If I use more data, more tasks in training, will it further help? Now that's where natural instructions V2, version 2 came in. Okay, so this was like 1600 tasks and 73 categories, 74 domains, 43 languages. They just took second version. I think this has 70, 80 authors, this particular paper. And huge, they took, I mean, translation, program execution, question answering, generation. And this was much, much larger than whatever were the previous other data sets on instruction fine-tuning, this particular natural instructions V2. Same group, Sarup Mishra and LNAI and Arizona, Washington. So this is the example. So the task type is co-reference resolution. This simplified it further. This is a definition. You are given a question containing a blank and two options. Pick the best option to answer the question. Answer with A or B. So this is the input, the output, and the explanation. Okay. Input, output, explanation. Positive example, negative example. And then they give an instance. And this is where they will train the model to output just A. Right? It has to just output A. Right? Valid output is A. So definition, positive example, negative example, and an instance, and you generate an output. Like this one was dialogue act recognition. So you are given 4 sentences, a bot sentence, bot role, user task sentence, user role sentence, classify given sentence into one of the 47 different domains. And they actually gave all the domains name inside the instruction, right? Then, positive example, output, what is the classify into one of the 47 domains? They said order pizza. And you give some explanation, input, output, explanation, and then input. And they have to predict movie listings as an output. Dialogue act recognition task. It's a classification problem. You are given a sentence. What's the intent of the dialogue? Question and rewriting. So it's a disfluent question. And you have to convert to a proper question. Some interruptions. So like, why was and where was the line regulated with an upper canal? Typically, it happens with when you're interacting with Alexa and other kind of systems, right? There are interruptions. So the task was your input may be interrupted question. You have to convert it to an uninterrupted question, right? Fluent question. Where was the line regulated with the upper canal? That's the input output. And then given this input, you have to produce this very output. Make it a fluent question. So you see, they created this all sorts of different tasks, right? A lot of people, they together did that. And what is the model that they trained? They trained TK instruct. So previously they were using BART model. Now they used T5 and fine-tuned T5 model. So it's fine-tuned T5 model with all these instructions. And they also used MTK instruct, that is MT5, they do multilingual T5 and fine-tune it with the instructions for multiple languages. And if you see the performance, English and cross-lingual tasks, so this is the instruction tuned models. So in Instruct GPT was OpenAI model. Instruct GPT also used PPO, some RL algorithm, but TK instruct and MTK instruct were only instruction fine-tuned, no RL. And they found they were doing better than Instruct GPT even. So Instruct GPT was the precursor to ChatGPT. Before ChatGPT, OpenAI came up with Instruct GPT. That was a model that was trained with instructions and other things. So yeah, I mean, this was some impressive numbers that they found. And again, in scaling, what do you see interesting in this picture? How does the performance scale with number of training tasks, number of instances per training task, and number of model parameters? So it's important if you use a larger model. Larger models can understand instructions better. It's important if you use a lot of varied tasks. But what is not important? What is not crucial? You don't need multiple examples per task. Like for the same task, you don't need many examples. So if you have more examples, it doesn't help too much. Doesn't scale with the number of examples. What you need to scale are number of training tasks and number of model parameters. And that's why you will see all the instruction fine-tuned models recently would be having very large models, this Llama models, 7 billion, even further, very large models, and they will use a lot of tasks, a lot of different training tasks, not just few, right? They will have a lot of different possible tasks. They help scale the performance better than instances per training task. And they did some ablations and they found something interesting, like if you just use definition and two positive examples, that is quite good. Definition and two positive examples, that typically does quite well. This is what you'd use in the testing time, what you use in the training time. So this def plus pos2 was, I think, quite good. Def plus pos2 in training, def plus pos2 in testing, they typically worked very well. Definition and two positive examples, training, testing, and that typically worked well. There were other cases also like this one, I think it's better than anything else, but yeah. Def plus pos2 in training, def plus pos4 in testing. So roughly same idea. Negative, again, did not help too much. Negative, it's not bad, but just if you have positive example, that is sufficient, sort of. Then this showed that they are very quick learners also. So you can further fine tune them. So till now we have seen cross task generalization. You train on some task, test on a new task. But what if I say, okay, for the new task also I will train them with some data. So they are also quick learners. So you can give a new task with some examples and they will learn quickly. So like this is the multitask fine-tuning of T5. You give separate tasks without instructions. So this time when water freezes, the water expands. Answer is freeze. Global warming will never hurt anyone. Answer is disagrees. It's not clear why, right? But if you look at the construction, it will be clear. In this task, you need to write a topic word from the given fact. So freeze is a topic word. Read the passage, find if the passage agrees, disagrees, or is neutral. Example fact here. So it disagrees. Right? The sentence is a disagreement with something, never hurt anyone. So it's a disagrees is the answer. Once you know the instruction. In T5, you only train like this: input, output, input, output. In TK instruct, you will give the instruction, example, and then this fact and then the answer. And what they found, just with 6% of training data, they will get comparable results to SOTA. And with 7%, they will outperform with 100% of training data in the issue of the art. So you give full data here versus you give 7% of the data here, 7% of data will do better than 100% of the data in T5 without instruction finding. That was the finding that they had. If you give the instruction, that helps. Right? Like here's in the summarization task, I think T5 model, use all training data, fine tune it, you get a RUGEL of 17.99. And TK instruct their model, no training data itself gives you 54.3. 6% of training data gives you similar. 25% samples will give you much improvement. So they are now, once you have this instruction fine tune model, you can even fine tune it on the tasks and gain performance. It can do cross task generalization. It can perform good from very small number of samples also. So yeah, they showed if you give number of training samples, the performance just keeps on increasing. Even with 100 training samples, it's comparable to SOTA. Okay. So I'll continue for some more time and then there will be hands-on. Okay. So I'll do a quick recap about instruction tuning to ensure that you are on the same page. It's a new topic for many of you, as you understand, right? But just want to ensure you understand the basic part about what is instruction fine-tuning, right? Compared to what you know, I mean, in the context of pre-training, fine-tuning, LLMs, where does that come in? So what I'm showing you is a page from OpenAI. This is the blog post that they shared after they showed InstructGPT. They came up with InstructGPT. That was before ChatGPT, InstructGPT, right? And they showed what is new there, like what's new in the chat models compared to the previous encoder only, decoder only, encoder decoder models. What's new? So they give this example on their blog post. Explain the moon landing to a 6-year-old in a few sentences. See, that's how you want to converse with the language model, right? Like somebody was asking, like, what is our goal? Goal is that you want to converse in the same way we do, right? So you want to ask things like that. Can you explain or can you summarize this particular article from a point of view of a doctor or a patient? You want to do things like that. Now, what GPT-3 does, you see the completions, but the multiple times they try to prompt, explain the theory of gravity to a 6-year-old. What is it doing? It is in next word prediction, and it is somehow trying to generate same kind of sentences. It's not clear that this is an instruction that is given to me, and I have to do an explanation, right? It's generating explain the theory of relativity to a 6-year-old. Very similar sentences, but it's not what you wanted. And then they showed a contrast of what their model, InstructGPT, does. And that's what you would have liked. People went to the moon, they took pictures of what they saw, sent them back to the Earth so that we could all see. 6-year-old, yeah, this is what you can say. So I'll show you one or two more, and then I'll tell where this instruction tuning fits in. Okay. So write a short story in which yeah, I think the prompt is not being seen here. This is the prompt. Yeah, the prompt was about write a short story about a frog or something, and then it again same way. It started writing other things, write a short story about this, that, and so on. While InstructGPT actually gave you the story. And so on. They showed some examples. Okay. So what are we seeing there? There is a gap in the model's capability of following instructions, even with the most capable model GPT-3 at that point of time. It could not follow instructions properly. Now, that's where to go towards a chat assistant, there are two phases that are followed. So you take any model, say decoder-only model, say GPT, whatever. You take a decoder-only model, base model, and the first thing you do is to do supervised pre-training. I don't know if you want to call it supervised or not, but pre-training. I'm putting a question mark because you don't need data. I mean, you don't need labeled data. You can just take whatever is available on the web and semi-supervised way, self-supervised way, you can pre-train. Self-supervised, you can pre-train. Lot of data, and you need a lot of data. That's always the first step. And then previously what you learned, once you have a model, example BART T5, and so on, you can then fine tune them for the task. Now, but they don't follow instructions. If you do that, they don't follow instructions, right? To make them follow instructions, there are two phases that are done. First, get a lot of instruction data. We saw examples of how do you get an instruction data? Definition of a task, positive example, input, output. So a lot of tasks. And then what you do, you just fine tune them. Supervised fine tuning. With instruction data. So it's exactly what you were doing with T5 and BART earlier also, right? There's no difference except now the template will be different in which you will feed it. So earlier here you were feeding, but input goes in encoder. If it has an encoder, output goes in decoder. Here, instruction plus input will go into encoder and output will go into decoder. And you will again use cross entropy losses and everything else to fine tune your model with instruction data. This is also known as instruction fine tuning. So that means whatever you learned about fine tuning is valid for instruction fine tuning, except that your data is instruction data. Your input is instruction plus input, and output is the normal output that you wanted for the task. And the hope is that by doing this, once you have fine-tuned a model and you call it instruction fine-tuned model, examples of these models, like TK instruct. We saw TK instruct. And we will see FLAN model. FLAN-T5 is an instruction fine-tuned model. FLAN-T5, from T5, you started from T5, fine-tuned it on a lot of instruction data, you made FLAN-T5. TK instruct, you started from T5, lot of instruction data, TK instruct. So this is one step. And then the next step that you do, second step you do, you try to align them to human preferences. Align models with human preferences. So you will take the data, you will ask the humans to rate the output, good, bad. You use some RL, or there are many approaches to further tune the model. Okay, that is and that's where you get all your models like ChatGPT and so on. Instruct GPT was also in the same category. Instruct GPT. Okay. So what I was saying, today we are seeing instruction fine-tuning. What is instruction fine-tuning? It's simply supervised fine-tuning with instruction data. To put it like in plain words, it's simply fine-tuning with instruction data. Right? Instruction has an additional instruction prepended to the input. And then you fine-tune it like you do. And how do you do this? This you will see tomorrow. Okay? This is coming tomorrow. So just to put things in perspective, where we are. Any questions on this part? Right? Then I will show FLAN model, like what did FLAN model do? But this is where the things are. Okay. Why we are doing it? Because you want models to follow instructions, to behave like it, conversation assistants, right? Chat models. But we are still not very close. I mean, they are doing some things, but we can't say they are following instruction like we do. There's a lot of work going on and needs to be done in that field. Yes. Fine-tuning. This is the normal pre-training. I mean, as I said, I put a question mark, you can call it self-supervised also, because you don't need labeled data. You just need data on the web. You can do mask language modeling, span corruption and prediction like you do in BERT-T5. So you need a lot of data. That's all. Plain data, not labeled data. Okay? So no labeled data is needed. And usually lots data, this data is much smaller. Maybe this will be 1% of that or 5% of pre-training data, roughly. Much smaller than what you did for pre-training. Pre-training gives you the general ability to understand language. You do next word prediction, in that you learn language. And that's where you may try to follow instructions. right? You can try this before, but typically that may not work so well unless you have as much data with instructions as you had with pre-training, right? I recently saw an archive paper came instruction pre-training. I don't know how much data they are using. I haven't read that paper, but they were doing pre-training from instructions. So yeah, maybe they got too much data. They can do instruction pre-training, but till now they do supervised pre-training, then instruction fine-tuning because they didn't have sufficient data for instructions. This is labeled data, no? This is labeled data. Yeah, that's what they did. These people, that's what they did. I'll show you like FLAN, how they did it, right? But you have to have labeled data here. In instruction plus input as in the encoder, output decoder, assuming encoder-decoder architecture. Yes, yes. Again, there are phases of a reward model, and so they have two phases there itself. Yeah, no point in talking about that today because tomorrow you will hear that. So yeah. So then let me just show another model. We talked about TK instruct. Let's talk about FLAN model. So this came from Google. So they had this PALM architecture also, but I don't see people using PALM too much. But at that time, they used FLAN with T5 as well as PALM architecture. So what they are doing, so fine-tune language models on 1.8 thousand tasks, phrase as instructions, and evaluate on unseen tasks. Same thing. So these works happened some sort of parallel. Like when Google was doing that, the other people were doing supernatural instructions. So these were parallel works. Okay. So they will train with a lot of tasks and inference on unseen tasks. Okay. Please answer the following question. So now see, they had smaller instructions, right? They didn't have very elaborate instruction that we were seeing earlier in supernatural instruction and natural instruction. They had much elaborate instruction. They didn't use much elaborate instructions. So how did they get so much data set? So they anyway took everything of natural instruction V2. So that had 1554 tasks. And from data set, they created many tasks. Now this is something like more of a hack, you can say. So what they will do? So you know what is the square data set? It's a reading comprehension data set. You have a paragraph, a question, and a span, that is the answer, right? So for example, what they will do, they will take the square data set and create many tasks like extractive question answering, that's the normal task. Extractive question answering, find the answer from the paragraph. But question generation, I can use it for question generation, right? I'll take the paragraph, I know the question, so I can create a question generation task from this. So like that, they expanded the number of tasks. Context generation, I have the question, what is the context of that? I mean, they created tasks in this way. So task is a unique data set task category. So from the same data set, you create multiple task categories. That's where, I mean, a lot of hack, lot of things went on. So that's why they created a lot of different tasks. Data set and category together is a combination, is a task. Okay. Same data set may have multiple categories. Like here, squared can be used for question answering, query generation, context generation. And then they used natural instruction V2, Muffin was another data set. They took all that and fine-tuned on this, like a squared can be used for QA and question generation. And they had some held out data tasks that they did not use in fine-tuning. Very similar setup as the others, some cross-task generalization, how well they will do. Okay, so trick is clear. They will take data sets, create multiple task categories. And that's how they have a large data set. So like another example of how they generate template. So this is the entailment task. You have premise, hypothesis, and target is entailment or not entailment. Yes or no? So they create multiple templates. Premise is this, give the premise, based on the paragraph above, can we conclude that question mark? Give the options. Under template, premise, you write this, can we infer the following? So change the words and created much more data. Read the following and determine if the hypothesis can be inferred from premise. So you see they are changing some template and creating some copies, and right, like that's how they created multiple templates and multiple tasks. And that's why it's not like they are following one kind of instruction, they did varied kind of instructions. Sometimes instructions come, say, in between the input, like premise, then the instruction, then the hypothesis. Similarly here, instruction first, then premise, then hypothesis. So different variations they tried. And all this is part of their training strategy. And then they also use chain of thought, right? Chain of thought, I don't think we have covered chain of thought, but it's just a prompting mechanism of asking, answer the following yes and no question, and can you write a whole haiku in a single tweet? Answer the following yes and no question by reasoning step by step, and they also do some reasoning. So here, just say yes, they will do some reasoning. So instruction without exemplars, with exemplars, without chain of thought, with chain of thought. Again, 2x2 matrix. So more tasks with training with chain of thought, without chain of thought, examples and no examples. Okay. And they used FLAN-T5 models and PALM model, their other architecture. So PALM is just decoder and T5 is encoder decoder architecture. Now you see the pre-training time and the fine-tuning time. So roughly, as you can see, the fine-tuning time is very small compared to the pre-training time. 1%, even 0.1% sometimes, 0.2%. Here 1.6% is the maximum. So whatever time you have to give for pre-training, you have to give just 1/50th of that, or even less than that, for instruction fine-tuning. Okay. So that means with some additional complexity, same model, the number of parameters doesn't change. You just instruction fine-tune it with 1 or 2% of the time you used for pre-training, and your plan models are ready. Your instruction tuned models are ready. Right? That was the idea. And then how did they improve? You can see the improvements happen with the scale. So if you use, say, something like T5XL, right? A huge improvement compared to T5XL versus FLAN-T5XL. 3 billion parameters, so huge improvement. Roughly, yeah, I mean, many cases double or even more. And even if you use larger model, more improvement. Did not have very similar kind of improvements in PALM, but still very insignificant, like 50 to 59.1 and all. So, and this is what? It's a few shot prompting accuracy. That means you pre-train on some task, held out, you have some held out tasks. On the held out tasks, you just do few shot. Right? You give instruction with few examples, and that's all.
Not fed in the base model. PALM is the base model.
But they are both base models, not both T5 and PALM are the base models. They were not instruction tuned at all. So these instructions were not fed. So this was like a lot of improvement. So just by instruction tuning, but they had a lot of instruction tuning data set also. Now, so in general, people have tried to create a lot of data. So you see, it's a very laborious process creating these data sets, right? But so we talked about natural instruction. It has 1600 tasks, which multi-instruct. And there are other people have created like P3, Big Bench, Dolly. So we'll see this example of Dolly. So they also 15,000 instances, not much. Like what they did in Dolly, they will create an open source follow-up of InstructGPT. So they created 15,000 instruction fine-tuning examples, like open question answering. Why do people like comedy movies? Like these are very popular. People typically want to ask this to the chat agent. So they created some open question answering, closed question answering. They will give the context and then the answer. Wikipedia, information extraction, summarize, brainstorming, classification, creative writing. Like these were some very popular things, creative writing. So they did that and created a data set. Like, what should I do on a free afternoon in San Francisco? and people will get response, and they will fine tune on this, right? I mean, just open question answering task, creative writing task. Write a haiku about how much I love pickles. Again, somebody will respond. They will use it for fine tuning. Extract all the dates mentioned in this paragraph, list them using bullets in the form, date description. So that's what they did. Take the paragraph, write. So, I mean, so what you see here, again, human labeling, right? So too much human labeling required. So that is why instruction fine-tuned data sets are there, but they're not in that scale as you have pre-trained in data set, because they require humans to label them, right? So, and it's difficult to increase the task diversity and complexity after a certain point. So even after all these hacks, they could only have a fixed number of tasks. So later on, what people have tried, can we generate instruction tuned data set automatically? Can large language models generate instruction fine-tuned data set, right? That was the next effort. So same team, say Swaroop Mishra and all. So what they tried, self-instruct. You do self-generated instructions. Now that's even on a high level. I mean, that means my LLM will generate instructions for me. I'll use that for pre-training another LLM, right? So humans are out of the loop here, but they won't be, I mean, various parts. So what they do? They said, okay, I'll take some examples. So idea is that if I can show some examples to LLM, this is how an instruction looks like. Give me similar instructions. It will give me similar instructions, right? And I'll create diversity in my instructions. So what did they do? They started with 175 tasks from their pool, one instruction, one instance per task. Okay. They create a task pool that they will keep on increasing. And then the language model, they will prompt the language model that you see some example of tasks, create a new task like that. Okay, I'll show you the template. Like, give me a quote from a famous person on this topic. Then they found out the task can be classification task or non-classification task. Classification task, the output label is limited. So they would do differently for classification instances and non-classification instances. So they then classify if this is a classification instance or yes or no, classification type or non-classification type. And they do things differently, do some filtering and put it to RAS pool and continue this process. Okay. And they use GPT-3 as their language model for doing all this. So let's see, step by step. Generating instructions. So how do they generate instructions? So they will initiate the task pool with some 175 tasks. And for every step, they will sample 8 tasks from the pool. Initially, all 8 will be from 175. Later on, 6 will be from human written, 2 from the model generated to create diversity. They'll give this task as prompt and say, okay, now come up with a series of tasks. Task is given, task 9, and let the LLM generate task 9 onwards. So it will generate more tasks. Okay. So now what will happen? The LLM has generated tasks. Then they want to find out if it's a classification task or non-classification task. What they did? Okay. The tasks that have a small limited output label space, they are classification tasks. And again, use the language model, prompt in few-shot way to find out if it's a classification task or non-classification task. They used 12 classification instructions, 19 non-classification instructions as examples. So can the following task be regarded as classification task with finite output labels? Task given a personality and the job. Tell me if I would be suitable. Is it a classification task? Yes. Example of a time when you had to use your sense of humor. It's not a classification task. Replace the placeholder in the given text with the appropriate name entities, not a classification task, like that. So they had, see, only instructions, not input output. First step was only to generate instructions, no input output. Okay. So they are generating these instructions, just the task, right? And it will be the classification, non-classification. Now, why did they distinguish between classification, non-classification? They will, next step will be separate from them. Why? They found out if they, so what will happen? See, once you have instruction, what is the next step? Once you have instruction, what is the next step in data generation? Instances. Once you have instruction, generate input output, right? Now, the problem with classification they found, if they do that generate input first and then output, classification was somehow biased towards some popular classes. They were not able to generate instances for all the classes. So classification, they will do output first. So generate, oh, this is the output I want, write a sentence about it. Okay. So step 3. So given the instruction in the task type, generate instances for each instruction independently. It was challenging because now you have to find out what is the task, what is the input you need, what is the output you need, right? Like this. Give me a quote from a famous person on this topic. It's not a classification task. So input, give a topic. First, you have to give a topic. That's what you have to generate. The importance of being honest. And then you generate an output also. So this whole thing is being done by the LLM. First, you generate instruction, then it generates this input-output pair also, right? So in multiple steps, they are doing it. First, generate instruction, then generate input-output examples for the instruction. For classification, what they will do, they will actually label all the classes. They will have prohibition and so on. All the possible classes. For each class, they will generate the text, input text. For each class, they will generate the text. Okay, that way they will keep it balanced. So Y2 models, they found out they can be biased otherwise for some classification tasks. And then once they do, so this is the template. So this is come up with examples for the following task. Which exercise are the best for reducing belly fat at home? And this is like the output. Turn down a job offer by sending an email to recruiter, explain the reason, right? I mean, these are very, very common. People send emails without even changing the field sometime now. After ChatGPT, many of us get emails without changing the placeholders. But yeah, I mean, this is what is generated by the LLM. So either task, you generate the output. No input is needed for this. And now you give task instruction for the target task. You have the instruction that you know is non-classification. You put the instruction, let the LLM generate. This is just a prompting strategy. These are all examples. If this is the task, this is the output, task, output. Now, given this task, give me the output. Output first, classification. Given the classification task, definition, and class labels, generate an input that corresponds to each of the class labels. And so like classify the sentiment of the sentence into positive, negative, mixed. They'll first give the label, the output, mixed, then we generate a sentence. Enjoy the flavor of the restaurant, but the service was too slow. Class label, positive. I had a great day today, weather was beautiful, and so on. Negative. And then they will give some more examples, and then your actual task, and you have to generate all labels, all sentences. Output first, then input. Output, input. So in classification, they reversed it. Output, input. Otherwise, they will have input, output. And then they filtered. They said, okay, it should be diverse. So whenever they find an instruction that is having a similarity to any previous instruction, they will remove it. Very common thing that you want diverse instruction. Something is very close to an already existing instruction, you remove it. Then exclude instruction that contains some specific keywords, image, picture, graph, because they are not processed by LLMs. And filter out those that are same input but different outputs. And some heuristic to find out invalid generations, like too long or too short. Repeat output is same as input. So like that, they did some filter. So 4 steps. Generate instructions by prompting, find out if they are classification, non-classification. Accordingly, do input first, output first, then you filter them. And you get a lot of data. And then what happened with that? So these are some examples that they generated. Is the instruction input output that the LLM generated. Given an address and city, come up with the zip code. And then input is this, output is everything is generated by LLM. Instruction, input, output in multiple steps. How to write a code for converting degrees to Celsius? Input is not required, just the output. Write a letter from the perspective of a cat. It's a very interesting instruction. You can just read this. I'll pause. It looks like a nice letter that the cat will write to the owner. Okay. So overall, they started from 175 tasks instances only. And by this whole process, they could generate 52,000 instructions automatically, right? And there were classification, non-classification. And what was the impact on the performance? So what we are comparing with, so you have GPT-3. So GPT-3, Instruct GPT-3, they give up to here. But now you can use GPT-3 that is fine-tuned with self-instruct. Okay, so they were able to fine-tune GPT-3 with self-instruct. Self-instruct is the data set they generated. And then they supervised fine-tune it on the Super NI, that the manual data set. And this was doing better than just GPT-3 plus Super NI training. So it was outperforming that. So if you have more tasks, you can do different things. And GPT-3 self-instruct was very comparable to Instruct GPT already, 39.9 and 40.8. So yeah, vanilla GPT-3 was very poor, 6.8. But just from GPT-3 to GPT-3 self-instruct, 6.8 to 39.9. Just by using their own data set, they went from 6.8 to 39.9. All manual, all automatic data set, 6.8 to 39.9. And then further on, if they added Super NI training, they went further. So this is where the field again said, okay, so we can have synthetic data sets. Why do we only worry about human data sets? Let's have synthetic data sets. Self-instruct has shown that they can be used. And I don't know if the battery is gone. So one of the famous model, alpaca model, that just came around the time, they did same strategy. What they did, they used this Da Vinci GPT variant. So again, 175 seed tasks. They modified the self-instruct pipeline slightly, generated 52,000 examples automatically, and supervised fine-tuned llama model and came up with alpaca model. Okay. So this is an example seed task. Brainstorm a list of possible New Year's resolutions. Example generated task. Creative ideas for designing a conference room. So alpaca is again a very popular model. Is just instruction fine-tuned over llama model by generating all these examples automatically, right? No human data. And in 2022 itself, this picture is taken from this paper, FLAN paper. That's what they are saying ours. So October 2022, by the time you see it's a huge collection of this instruction data sets, right? Which one we have seen? So we have seen FLAN 2021. We saw this FLAN natural instruction V1, natural instruction V2. It's called supernatural instructions also. And what are the models? TK instruct, FLAN models, right? But then there were so many other things that came in. Like Bloom's was a model that was trained for multilingual translations and all. Like Bloom's is one of the very good model if you want to do translations. And then there were unnatural instructions, self-instruct we just talked about. This is huge variation. That is up to 2022. Today is 2024. I mean, this is We're talking about 2 years back. So immediately there was a huge boom in the kind of models on instruction fine-tuning. And among these, if you see the LLM generated data sets, self-instructed was the first such paper, but then unnatural instructions came in. Muffin, Dinosaur, Wizard LM, long form, there are many such data sets that have come, all synthetically generated. Different strategy, like one paper, what they will do, they will take a Wikipedia paragraph, and they will create an instruction based on that. I forgot what was they saying. I forgot exactly. This was this Dinosaur paper, I think. Long form paper. And what is the strategy that they use? So they have to play with 3 things: instruction, input, and output. So what they can do for the same instruction, they can have multiple input output. Instruction is same, you keep on having more inputs and outputs. Or you don't even have the input, just instruction and outputs, or multiple instructions you apply on the same input and you get different outputs. Like I1 x y1, I2 x y2, I3 x y3. So that's how they scale. Either they scale in the by putting same instruction across input outputs, or same input across multiple instruction getting multiple outputs. So that's how these models have scaled. Okay. So in the remaining few minutes, what I will do, I said that, yeah, FLAN-T5 you can use for instruction tuning, but what about its capability of supervised fine tuning? Is it even good there? Like if you want to do supervised fine tuning. So I'll just show some experiments that we did for FLAN-T5 for finance domain. Okay. Yes. Yeah. Yes. It's a supervised fine tuning with instruction data. Yeah. That's correct. No. Fine tuning is typically always supervised. Okay. So no, pre-training, I said pre-training also you are changing your parameters, but the data need not be labeled. You just use raw data with some pre-training objectives and you can do pre-training. So you can call it self-supervised. So you don't need some labels for that. You create labels from the data itself. Okay. Any questions up to whatever we have discussed till now? Yeah. You have to think in terms of continual learning sort of scenario, that first you are training them to do a very specific task, predict next word, but they cannot do next word prediction unless they know a lot about the language, about the world, right? They need to have a lot of knowledge to be able to predict the next word correctly, right? So that's what knowledge you're getting inbuilt in the models by pre-training. There are, of course, limitations in what this will happen because you have to do next word prediction always, right? Some limitations get imposed, but you're also making them learn a lot about the language. And this is the thing that you are using in the instruction fine-tuning phase. They know the language now. And that's why they can reason. They can try to reason, or they can look as if they were doing reasoning. They can behave as if they are reasoning. We don't know if they're reasoning it correctly, but they can imitate as if they are reasoning. That's what is happening. No. Yes. Now there are Indian.
Not translated versions of these.
I think most of them are translated versions. Yeah.
So the context is
Hmm.
kind of.
Most of them are translations. Yes. True. Okay. So yeah, I mean, just no, go ahead.
One, where is the what would be
Multi?
like when we are giving
No, what do you mean multi-shot learning? No, what did you say?
when it comes to instruction finding, we basically have an instruction in our mind and we are getting a task completed result or the result of that instruction to the LLM. Now, when it comes to multi-shot learning, when we have multiple contexts given to the LLM, so there will be instructions as well, right? Which we are
No,
getting to them.
typically there are no instructions. Just input-output examples. Input-output. Yeah.
But will that be
No, that will become instruction fine-tuning. Instruction can be as simple as just the definition of the task.
so in the prompt which will be having a specific keyword instruct, rather than
Yes.
learning there need not be any
Just give the input and the output. So here you'll have some separators about instruction, input, and all. You'll give some keywords there. Okay. So yeah, talking about some of the works that we did with FLAN-T5 on the finance domain. So this paper just got presented at NACL, I think few days back. So Shubhendu had traveled to NACL, the first author, and the last two authors are here, Professor Saptarshi and myself. So this was parameter efficient instruction tuning of large language models for extreme financial numerical labeling. And this work was in collaboration with GS. There are many authors from GS, like Kaustav and Manju and all. So what was the task for us? See, in financial reports, what we found, so reports are like that. And they would have some numericals, like 192 million is a numerical. And they have meanings. Numericals have specific meanings. Now they have an actual taxonomy where they know this 192 million has a specific tag. It's a US GAAP metric, retained interest fair value disclosure. Very specific financial tag, right? And it will have a documentation also. It will have a whole explanation what that means. Now, people had, when they put the reports, they had to manually find out what is the correct tag it, right? It's a huge cumbersome process. So we thought, okay, let's tackle this problem. Can we use machine learning somehow to solve this, right? Now, what were the main challenges, right, in solving this? It looks like, okay, tagging task, you have a numerical, you have to tag it with some entity, right? Like we do in NER, name entity recognition. You have a sequence, find out the name entity for each word. So what was different here? Like just to give an input-output format. So suppose this is your input. Upon adoption, the company recorded 2.7 billion of net deferred tax, etc. And you have to say that there are three numericals, 2.7, 128, 2.6, and what are their tags? Right? For each numerical, what is the corresponding tag? Now, we took some 10,000 annual documents that were publicly available. And so around 2,000 companies were involved in those 10,000 documents. And we came up with an annotated data set of roughly 1,42,000 sentences. That were numericals, 79,000 sentences. And what you see, we had 2,794 labels in the data set. So that many different labels would be present. Now that's where the problem becomes difficult. But typically when you do NER or other sequence labeling problems, you don't have so many labels. You typically have like 8, 10, 20. This was like 2,000 labels were too many. And you can see, I mean, there was, of course, heavy tail. Like some labels were having a very high frequency and some were like appearing 1-2 times. It's typical problem. Now, and yeah, so you see the number of entity types, number of unique labels. So compared to other data sets that were there, the maximum we could find around were like Finer 139 that had 139 labels. That was also the same data set, but on a subset, 139 labels only. No, not links. So it's like, what does this numerical mean? 637.5 million. So there's a taxonomy, US GAAP taxonomy, where they have defined certain terms, like this one. Business combination consideration transferred. Business combination consideration transferred equity interest. Now what they mean is also something interesting. So they have a documentation. Common stocks, shares issued. They will have documentation. What does that mean? Total number of common shares of an entity that have been sold or granted to shareholders. So they have some financial meaning. So each numerical was tagged with one such label. There were 2000 plus labels. Does that answer? No, not hyperlink. It will be like a HTML. It was in HTML. So you click on that and this window will appear where you will see this information. Not to a page, not hyperlink to page. So what I was showing in the first slide itself, it will appear like this. Like this. This window will come and will give you information about this tag. Okay. And yeah, same sentence may have many such numericals, some maybe, and see something may not have a tag like 309.005.272 has a tag others. It doesn't have any tagging in the set. Right? So, and a sentence had many such nations. Common stock shares authorized, common stock shares issued. Just one word of difference, right? So overall, it was very challenging problem. 3000 labels, one word change, and the meaning can be entirely different. Now, and sentences were like typically do not have enough context, one sentence, having multiple numericals. Like here, if you see the sentence, if you read the sentence, you will not even find out why this was labeled as workers' compensation liability, current and non-current. It was not clear from the sentence itself. So there were issues like that. So now, so one thing we said, okay, fine. Maybe the names are not sufficient. We can use documentation of the tax. So that if it's a documentation that was much more detailed. So we can use documentation. So that was one thing that we thought we can do. So even we, like first two tags differ by only one word, but their documentation was entirely different. This was giving all detail. Okay, now. Let me pause here, let me ask you. Now that you have been instruction fine-tuned for some time, right? So how do you think you can handle this problem? How would you tackle this one? I've just told you the problem, right? That you have this document, and in document there can be numericals. They will be tagged with, say, from a set of 3000 labels. They will have documentation also that you can use of. So what kind of approach you would use? You have data, sufficient training data.
First step would be saying that start the annotation. And
So annotation in this case, I'll just answer that. Because we directly downloaded the data, with each numerical, we had the label. So annotation was, we didn't have to do manually. We could just get the data directly. Yes.
So, and the thing, after a click on every number or every figure, there was a hyperlink.
Yes, and we crawled that, and then we got what is the actual label.
$1 lakh, $1 million, and then click on it, there will be a page. So, one way.
It's not a page, just a box, proper box. Yeah.
We can put those boxes, right?
That's what we did.
We can categorize the boxes and not the figures. the annotations are not important, but the box, the annotated box, the information given in the annotated box, like what the link or what are the dialog box. So now we earlier had 2000 some order labels, which came down to 139 by in the terms of those boxes, correct?
No, no, no. You will have a box with every numerical. You say the unique number of tags. There are 2,794 unique tags. Yeah.
But what about the dialog boxes?
No, no, dialog boxes have nothing. I mean, they are just structures. No, I mean, to show the visualizations. They're just visualizations.
But these are the annotated, but the earlier one. But this is something which I click on and then I get.
Right, and we crawled it. We crawled it. 192 means this. This is the label for that. Not a hyperlink. I mean, it's a pop-up box. No, but what do you what do you want to say? No, no, this is the ground truth tag. This is the tag. This is the tag. So we have this data, we have this tag. We also have its documentation. No, no, there is no click. I mean, you have data, you have labels, each numerical has a tag. You have that data, right? And tags have further information. Okay, let me ask, what is the default method you will try and use here? Yeah, something like that. They document numericals, you want to tag. Yes, that's all. And that's always the case. It will depend on many things, but the task is this, no? Input is given, each numerical you have to tag with a numerical, with it, one of the 2,794 labels. Hmm? Yes. See, in this case, we have a sufficiently large data set already for training, because 79,000 sentences we could get, and we didn't have to manually label them. They were already labeled, right? So, yes. Mm-hmm. So you can use the normal models, like BERT model. It will label each word with, like it does for name entity recognition, NER task, sequence labeling. See, no, but I'm saying training the model, given a new document, how do you label? That's the task. So you have to train and build a model that, given a new document, it can label the numericals. Yes, yes. True. So what we did, for example, here, we took an instruction fine-tune model, FLAN-T5. It's already instruction fine-tuned, it understands its instructions. Now we will give it a specific instruction. Read the following paragraph. Then we will ask, what is the tag associated with this numerical? Right? We can ask like that. So we will say some instruction, give the paragraph, then the paragraph input, and then we ask a template like, what is the tag for this? And then what is your output? Output can be the tag itself. But the problem was tags were differing just by one word, but they had huge differences in terms of what they meant. So rather than trying to generate tags, we tried to generate tag documentation. You try to generate tag documentation. Okay. So this was a training process. You take a FLAN-T5 model, instruction fine-tune it, further instruction fine-tune it with a specific instruction, paragraph, what is the tag for this model, and try to generate tag documentation. Okay. Documentation means each tag has a documentation. The problem that happened with this, at inference time, they will generate some documentation that may not exactly match. Because you're generating. It may not exactly match what you had in your labels. So what we had done again, some matcher. So whatever it generates, we find out what is the closest match in your documentation set. And that's how we do the task. No, we are saying generate a documentation. Yes. What is the label? You generate a documentation. We are not making it a classification task. Yes. It's a generating. It's a generating one of the documentations. That can be an issue, but typically what we saw, if the this was not a major hurdle, but that can be an issue. Yes, because this is how we feed the instruction. I'll show you the instruction. I don't know if it is visible to you. I'll try to. Here, read the task description. There could be multiple numericals in the statement. Each number may or may not be associated with a particular tag. Then, now read the following financial statement. Question, what is the tag associated with the numeral 1.4? That is what we feed as input. Then FLAN-T5 is fine-tuned. Of course, for fine-tuning with limited GPUs, we had to use some parameter-efficient methods. That will again be covered on 1st of July, so I will not talk about this. So LoRa and other methods can be used. And then what it generates is a possible documentation. Okay. Now it may not be in the list of the documentation that we have. So again, we have a matcher. So we'll try to find what is the closest match in our set. From some sentence embedding methods, we try to find the closest match, and we say, okay, then this has been the assigned tag. Corresponding to that documentation, what is the tag? That is my final output. So this was the process. Instruction fine-tuning, a FLAN-T5 model, and generating documentation. And finding the closest match in our set. And coming to main results, the first two models are BERT models. Finer, just use a BERT model and label the entities. So if you can see, the numbers are like 49 and 75, hits one and macro F1. And if you come to this model, FLAN-T5 large with LoRa, we already achieved 66, like 47 to 66%, and 75 to 89% in hits one. So it's a huge improvement. Even if you compare with T5, if you use T5 directly, the numbers were better with instruction fine-tuned model than using the T5 model. We also tried ChatGPT, giving some samples and all, but it was not doing well for this case because it did not have knowledge unless you give all the 2,794 labels, and there was no easy way of doing that. So we tried generating the documentation, matching, did not work out with ChatGPT. And because there are many, many things, you could also use attention XML, some extreme labeling thing that also did not do as well. What is the metric? Hits at one. So hits at one would be, so when you, because you are ranking, you're matching all the possible candidates, you can give a scoring, right? And hits at one means your top ranked output. Is that correct or not? So in ranking, you have this matrix: hits at one, hits at two, hits at three. So at top three, did you get the correct output or not? Similarly, at the first position, did you get the correct output or not? Okay. So use case was that even if you get a correct output in top five, you can semi-automatically label things. You can give it to human, and the human can say which of these five is correct. That was the use case for this. And you see, interestingly, what we were saying about instruction fine-tuning, we tried to see in the test set the tags that had less than 10 frequency. I mean, they occurred in less than 10 times in the training data. And they were tags that occurred 120, 200 times in the training data. So how much improvements we got? This is only showing the improvements compared to the attention XML baseline. You see, if we have less number of tags, with instruction finding, we got a huge improvement, like 35% improvements, right? Improvements were there, but not so much when you had high frequency already in the training data. So for the rare labels, instructions actually helped. So this was something, again, interesting. And then we saw ablation, like what happens, which module actually helps. So we found that 66 was the macro F1. If you remove the instruction prompt, immediately it goes to 56.46. So roughly 10% absolute improvement was coming from instruction prompt that we gave. And then if you remove the tag metadata, it was very poor again, 53.12. Tag metadata was important. If you directly try to predict tag name, it was not working. Because tag names were very ambiguous. When you have documentation, then it was much better. So even if you do instruction tuning, but have this confusing tags, it did not work. So both together, giving the tag metadata and instruction prompting were important for this to actually work. Okay. And we also saw zero-shot capability. What if I have never seen that label? Can it still generate, right? So you see, if you have doing it a tagging task, you can never do this because you have never seen that label. So how would you even tag it, right? But here, what you can do, you can generate documentation. You know all the possible documentations. Even if you have not seen a training time, this is okay, right? You're generating documentation and matching it to all the possible documentations. So you can still do zero shot. And we found it was not so bad. Zero shot also, it was doing quite well. Okay. And yeah, I mean, what time do we break and start for the next? 3:30? Okay, and then from the hands-on. Okay, so I'll just take maybe 10 more minutes. So similarly, we had this paper that is going to be presented in SIGIR. So this is instruction guided bullet point summarization of long financial earning call transcripts. Okay. So here, what was the task? So you have typically what happens, these finance in this companies, they do this quarterly earning calls. In these earning calls, they describe what happened the last quarter with the company and what is our plan for the next quarter and next year, where, what field we are expanding. So they do they call. It's a huge transcript. So our task was, can we find some bullet points? What are the main critical points, something like this. So this is from Motley Fool website, where they host all this earning call transcripts. So we found out that Reuters actually take this data, and for some of the articles, not for all, they create these bullet point summary. And this was very, very nice and clean. I mean, quarterly earnings per share is this much, quarterly total net sales is this much, versus this reported last year. They do some nice bullet points. So this became our task. Okay, fine, you have this very large earning call transcript, and you have to find the summary, right? So you have to summarize that into this bullet points. So it's a summarization problem. Now, what was challenging here was the compression ratio. So that is, if you see the ratio between the document, number of tokens in document versus the number of tokens in the summary, 100 times. So it's 100 times compression that you are trying to achieve with this summary. And this was among one of the largest compression ratio in the summarization data sets available. Okay. And this data set anyway we proposed in EMLB 2022, the ECT sum. This was a data set for bullet point summarization of long earning call transcripts. Now here we were seeing how we can use this instruction fine-tuning models for doing this summarization. Okay, so again, let me pause. So how would you try to achieve this? How will you try to approach this problem? So you have this long earning call transcript and you want to generate a bullet point summary like this. And you have some 2,000, 3,000 training data with you. So what would you try to do? How would you typically approach this problem? It's up to you. They are not exactly extractive because the phrases that are there were not exactly in the document always. But the numericals would typically be in the document. The phrases were not always in the document.
For each of the smaller paragraphs, you take a small summary, bullet point to it, and then forward.
Yeah. That's doable because the entire summary could not be fed in many models. You could not feed the entire document alter. So in our EMLP 2022 paper, we proposed an extract then paraphrase approach. First you extract important sentences, then you paraphrase into this bullet point form. We tried unsupervised methods, also some supervised method. Because you have the summary, you can find out which sentence in the document is closest to this. So you create some pseudo-label data set for this is the original sentence, this is the extractive summary. You train a model to generate that extractive summary, then you paraphrase from that to a bullet point format. So we did this extract, then paraphrase kind of model. Okay. So that was the previous kind of approach. We use T5 for doing this paraphrasing. So once you do extraction, you do T5 for paraphrasing. Now, what was different that we did in this paper? So yeah, it's a very long and complicated way, but what you can see is this FLAN-T5 coming in. So we now use some instruction fine-tuning. So we give the instruction, given the provided text, generate a concise abstractive summary. And we give a context. And the context here is not the entire sentence, but we extract. So we have an extractive phase and a summarization phase. Extraction and then summarization. Once we extract, we give it to the FLAN-T5 model with the instruction as the additional context. Now, how did we got the extractions here? So for extraction, what we did, so we took the reference summary, like Q2 non-GAAP earning per share is this. And we tried to generate some questions from this. So what question are you really asking? So what is the Q3 revenue and what is the revenue of FY revenue? I think that's not a good question, but yeah, of this financial year. But we generate some questions for each line of the ground truth summary. And then we find out what sentence in the document tries to answer that question. this is how we created this sample data set on extraction. From the questions, what sentences document answers, try to answer that question. And when we had all the questions, we tried to categorize into various themes, like topic modeling. So we found certain themes like revenue. There were some questions about revenue, about sales, about income. And then when in testing, what we do, so when we are given this whole document, we try to find out among these 30, which of the topics are really present in this document. Then we go back to the questions and try to find, are there sentences that are answering those questions? So we determine the possible topics in the ECT and topmost questions for each using cosine similarity. And then once we have the extracted content, we give it to FLAN-T5 model. So FLAN-T5 will get the task description and the context that has been obtained from this topic modeling kind of approach. What are the sentences that are, what are the questions that are important in this document? And by doing this approach, we found that from the previous method, we achieved very significant gains, like 0.467 to 0.557. So this was again very something very interesting, that with the instruction fine-tuning, it can also help in the normal supervised fine-tuning tasks. Right? So we were seeing it helps in cross-task generalization, but it can also have an improved performance for tasks where you have some training data. You can still use them and get much better performance. So, okay, with that, let me just end with the connection with the next topic. Right? So we talked about instruction fine-tuning. What's the connection with the next topic that we will have? So I think I have shown you examples like that. So typically, when you're doing prompting, you're typically saying, okay, I have some input and I'm saying, oh, give me a one sentence summary of that. It can do, but if you fine tune with the instruction model, it actually tries to converse. So sure, here's a one sentence summary of the story, and then it tries to give you the entire output. Okay. So motivation for instruction fine-tuning comes behind, the motivation is building a chat agent, right? So typically the LLMs that we are training, they try to reduce the perplexity of a large training corpus. Okay? So it's good at completing your sentence, right? But instead of just predicting the next word, we want it to behave conversationally, right? Some conversational feeling. And that's why we want to align the language model with the expectation of a human usually. Okay. That's where the key idea comes in. You fine-tune LLM on it, chat agent kind of training data, where you're really conversing. Yes, and that's what instruction fine-tuning does. So instruction fine-tuning is typically a method by which you can give an instruction and ask it given an input, perform the output. So yeah, there are many other names with which this goes. And we will see more about how do you do alignment after you do instruction fine-tuning. How do you do alignment with different methods tomorrow? Okay, with that, I think let me end today's session. Whatever I had to cover, they will be hands-on. So any final questions? I think I was happy to see a lot of interaction, a lot of questions from you. I hope I could answer some of those. But yeah, some of these were really important research questions, and we have to keep on seeing like how are people really trying to solve some very crucial problems that many are not even able to formulate properly. Right? Even formulating a problem is very, very important, as you understand, right? So I was happy that you were asking some very, very interesting questions in this domain. Okay. So yeah, any questions from your side? Now, are you saying you don't give the correct answer, but you give what, a half correct answer, a hint? That's still okay. I mean, that's not a negative answer still, right? You want to give a hint for the person. Yeah, but yeah, that's a use case, but I'm saying that's not a negative example scenario that you're seeing. Okay, it's more about you are just generating one step of the output, first step, and let the model complete, let the user complete the rest of the steps, right? So you can still do instruction fine-tuning where you say, okay, you have to just generate the first step of the task and not the complete steps, not the remaining steps. Yes.
If I want to extract my legal name and then put it inside the transformer, and also have the original text, put it inside the transformer. Do some extract the summarization techniques, extract some key phrases, put it inside the transformer, and then try to create and accept the subject. Right? So, clearly understanding how to actually input all these inputs inside the transformer.
No, that's where the instruction fine-tuning can help. No? So you can say, okay, this is the task, these are the relevant keywords, these are the relevant this, that. You give every information, then you say, now you try to give summarization. So you have to give it like an instruction. That's what we were doing. We were giving some information before in the instruction itself, then we are asking it to do the task. Extra information you can feed as instructions. That's how people do right now. You feed all this relevant context in the instruction itself, in the prompt. Yes, see, that is a model. Instruction fine-tuned is a model, right? You have to give some input and get an output. When you do input, output, you have to give the instruction. In the instruction, you can give detailed instruction. You give all the required information there. And if you have data, you can fine-tune it further for this. Yeah, PEFT is used for fine-tuning anyway. Yeah, PEFT is together with fine-tuning. And PEFT is a method by which you can fine-tune it efficiently. RLHF, I mean, if you have to do that, will be, I mean, too much, because then you have to have separate data, human preferences. For RLHF, you need some more things. You need some human preferences, like among possible responses, which one humans prefer, which ones they don't prefer. So you need some additional input for RLHF. But yes, instruction fine-tuning you can do if you have some data. Yes. No, you instruction tune it on certain tasks. See, what has been seen already, they are good at cross-task generalization. So even if you have not fine-tuned on some tasks, they do well on that. So that has been seen anyway in general. So I don't think that will be the case that you are fine-tuning on some task, they will forget. Because are you saying they have been trained earlier, you will train on new tasks now? Are you saying you will take FLAN-T5 that has been instruction fine-tuned on some task, now you will fine-tune it on a new task? Yeah, that's a good question. I haven't checked. I mean, if you instruction fine-tune FLAN-T5 for a new task, will it do some forgetting of previous task? They should not, but yeah, I mean, it's empirical. I don't know. Maybe they will. Maybe they will. I don't know. It does? Okay. He already has experience, so it does. Okay. Yeah, I mean, see, unless you are doing it together, I mean, because your parameters are going away towards one particular task, it may happen that they will do forgetting for previous tasks. That's possible. No, very simple intuition. No, I mean, this is sequence to sequence task. Your input is a sequence, output is a sequence. Any sequence to sequence task, you typically favor encoder decoder model. Like translation. Your input is one language, output is another language. You typically use encoder decoder models only. BART, T5, MBART, MT5, these are the typical models for translation. Summarization also falls in the same category. You have an input document, output is a sequence, right? So and typically it's abstractive summarization. So then you have to generate, right? So you will encode your document and generate a summary. So typically, I mean, NLP, in NLP, originally there were three kind of tasks. You either do classification, or you do sequence labeling, or you do sequence to sequence. Before anyway LLMs come, now everything is same. But so then there were different kind of architectures for each. Classification had separate, sequence labeling had separate, sequence to sequence had separate. So when RNN came, so you used RNN encoder decoder for sequence to sequence. Transformer came, transformer encoder decoder for sequence to sequence. But you will just use transformer, simple transformer for both of these, just the encoder. So this has been there for many years. Okay, so you use encoders for classification and sequence labeling task, encoder decoder for generation kind of tasks. Yeah. Nowadays everything is decoder based. Llama model, all these models are decoder based only. No. Summarization you can use Llama too. You can use decoder only models. Okay. So what I'm saying, this is traditional, but nowadays for everything you can use a decoder only model. You don't need an encoder because whatever you have to encode, you can fit as a prompt in the decoder. See what happens in decoder only model. We were just discussing in the lunch, like in the interval, right? So suppose you have to summarize. So you want to say, I have an input document and output summary. You just want to use a decoder only model, no problem. You'll feed the input, whatever, I mean, some formatting, the whole document. Then you say, okay, summarize, or whatever, summarize it to. And then you start generating. It's only decoder. So what will happen? Whatever you have fed, you will generate only, as Professor Mayank was saying, you only will generate key and values for these, right? You only need keys and values for this. K1V1, KNVN. But now, for each word, you will generate the query, and you will do attention, generate, and then also keep the key value, query key value. So now everything is happening at decoder. Whatever information you gave went into the prompt, but you can make use of that by the key value that they are giving. So you can use decoder only model for doing everything by giving appropriate prompt and task. Like we saw, like the first thing I showed, you can say, given a sentence, the class is, and you generate a word. You can do anything with the decoder only models. That's how they are default now. So if you see currently, very rarely people would use T5 or BART kind of models. They would go for just decoder only model. They are all the LLMs are decoder only right now. Any other questions? We could have used that of fine tuning, but we just use an unsupervised topic modeling kind of approach. So where we said, okay, given a document, we can find out which topic it belongs to and take questions for the topic. Then we find out which sentence the document answer those questions. That becomes my extract. We could have tried fine tuning also there, but we didn't. Just the topic modeling. Yes. Exit mapping was also not available there. No, it might have given a better performance if he had a supervised model. But there we didn't. We use supervision only when once you have the extract, generate a summary. There we use the FLAN-T5 supervision. That was completely supervised. The context was unsupervised, we extracted from the document. Okay, I think it's nearly time. So I hope you got some idea about instruction fine tuning, right? What that is. And tomorrow again, there will be a session on building the chat agent. So I think this will become very, very clear. What is the process of building ChatGPT? Right? So okay then. So then